Hello there, and welcome to Nightfall Science. Tonight, we drift gently through the quiet evidence that suggests life may exist beyond Earth. Let your shoulders ease and your eyes grow heavy. The universe is waiting. Let's begin. The first clue that life may not belong to Earth alone is remarkably simple. The universe seems to make the ingredients of life almost everywhere. No confirmed alien organism has yet been discovered. No distant world has provided undeniable proof of biology. Yet the raw materials needed for living systems are not rare treasures hidden on a single planet. They drift between stars. They gather inside meteorites. They appear in frozen comets, warm planetary atmospheres, and enormous clouds of gas stretching across light years. The chemistry of life begins long before planets are fully formed. Every living thing on Earth is built from ordinary cosmic elements. Carbon forms the flexible backbone of biological molecules. Hydrogen and oxygen join to make water. Nitrogen becomes part of proteins and genetic material. Phosphorus helps cells store and transfer energy. Sulfur appears in several essential amino acids. None of these elements originate on Earth. Hydrogen begins forming soon after the birth of the universe. Heavier elements emerge later, inside stars. A star is more than a distant point of light. It is a quiet furnace where simple atoms slowly become more complex ones. Under immense pressure, hydrogen nuclei combine to make helium. In larger stars, further reactions create carbon, oxygen, neon, silicon, and other elements. The most massive stars continue this process until their cores contain iron. When some of these stars reach the ends of their lives, they release their material into space. Some expand and shed their outer layers gently. Others end in supernova explosions, scattering newly formed elements across the galaxy. Those elements do not disappear. They become part of new clouds. The clouds collapse. New stars ignite. New planets gather around them. The calcium inside bones, the iron carried through blood, and the oxygen taken in by every breath all belong to this long cosmic history. Life is made from the remains of ancient stars. That fact alone does not prove that life exists elsewhere, but it reveals something important. Earth does not possess a private set of ingredients. The same elements appear throughout the observable universe. The chemistry of living things begins as ordinary starlight and dust. Carbon is especially significant because of its unusual versatility. A carbon atom can form 4 strong chemical bonds. This allows it to connect with many other atoms in long chains, branching structures, sheets, and rings. Carbon can help create molecules that are stable enough to endure, yet flexible enough to change. That balance is essential for complex chemistry. Proteins, fats, carbohydrates, and DNA all depend on carbon frameworks. On Earth, carbon compounds perform countless roles. They store energy. They form cell membranes. They carry instructions. They build tissues and allow organisms to grow. Carbon chemistry is not limited to Earth. Astronomers detect carbon-bearing molecules in the spaces between stars. These regions may look empty, but they contain thin clouds of gas and microscopic dust. Within those clouds, atoms meet on the surfaces of frozen grains. Energy from starlight and cosmic radiation encourages reactions. Slowly, simple molecules become more elaborate. Some interstellar clouds contain carbon monoxide, methanol, formaldehyde, and other organic compounds. In astronomy, the word organic usually means that a molecule contains carbon. It does not automatically mean the molecule was created by life. Even so, these discoveries show that complicated carbon chemistry can begin in places without oceans, forests, or living cells. It can begin in the cold darkness between stars. One of the most studied regions is the molecular cloud complex near Sagittarius B2, close to the center of the Milky Way. It contains a rich mixture of molecules, including several with relatively complex structures. Other star-forming regions reveal alcohols, sugars related to biological chemistry, and molecules that can become parts of amino acids. The universe does not need a living organism to begin arranging carbon into interesting forms. Chemistry starts the process on its own. Across long periods of time, these molecules become part of collapsing clouds. They enter the disks of material surrounding young stars. Some are transformed by heat and radiation. Others remain locked inside ice and dust. Eventually, they may become part of asteroids, comets, moons, and planets. A young planetary system is therefore not chemically empty. It begins with a collection of materials inherited from older stars and ancient interstellar clouds. The ingredients arrive before the world is complete. Evidence of this ancient chemistry occasionally falls directly onto Earth. In 1969, a meteorite breaks apart above the town of Murchison in Australia. Fragments scatter across the surrounding area. Scientists later study the dark, carbon-rich material inside. The Murchison meteorite contains a remarkable mixture of organic compounds. Researchers identify many amino acids within it. Amino acids are small molecules used by life on Earth to build proteins. Some of the amino acids in the meteorite also occur in living organisms. Others are uncommon or absent from familiar biology. This mixture matters. It suggests that the compounds do not come from contamination by earthly life. They form through natural chemical processes before the meteorite reaches the ground. Amino acids are not living. They do not reproduce or carry complete genetic instructions, yet they are useful building pieces. Their presence inside an ancient space rock shows that prebiotic chemistry can unfold beyond Earth. Space can prepare some of the pieces before a planet ever receives them. Meteorites preserve other important compounds as well. Some contain nucleobases, molecules related to the components used in DNA and RNA. Others contain sugars or chemical precursors that could participate in more complex reactions. These discoveries do not mean that genetic material is drifting fully assembled through space. They show something quieter and perhaps more meaningful. Nature repeatedly creates the same useful molecular patterns. The early Earth experiences frequent impacts from asteroids and comets. These objects may deliver water, carbon compounds, and other materials to the surface. Earth already contains many of these ingredients, but incoming objects add to the chemical inventory. The young planet becomes a meeting place. Material from stars, interstellar clouds, asteroids, volcanoes, oceans, and the atmosphere gathers in one environment. Energy arrives from sunlight, lightning, impacts, and heat within the planet. The chemistry continues. A similar process may occur on countless other worlds. Around many young stars, astronomers observe broad disks of gas and dust. These protoplanetary disks are the construction zones of future planetary systems. Tiny dust grains collide and cling together. Small clusters grow into pebbles. Pebbles become larger bodies. Over time, planets, moons, asteroids, and comets emerge from the disk. Observatories such as the Atacama Large Millimeter, Submillimeter Array, known as ALMA, study these distant disks in great detail. Some show dark rings and bright gaps. These patterns may be shaped by young planets gathering material as they orbit. ALMA also detects molecules within the disks. Water-related chemistry, carbon compounds, and other materials appear in regions where new worlds are forming. The same broad process that once creates the solar system continues elsewhere in the galaxy. Stars are born. Disks gather around them. Planets assemble from ancient dust. The universe repeats this pattern with quiet patience. Water is another important part of the story. Every known form of life on Earth depends on liquid water. Water carries nutrients, supports chemical reactions, regulates temperature, and allows molecules to move within cells. For a long time, Earth's oceans may have seemed like an exceptional gift. Modern astronomy reveals that water is widespread. Water vapor exists in interstellar clouds. Water ice coats grains of dust in cold regions. Comets contain frozen water. Asteroids hold water inside minerals. Icy moons preserve enormous reservoirs beneath their surfaces. Mars contains water ice at its poles and beneath the ground. Ancient valleys, deltas, and mineral deposits show that liquid water once moves across parts of its surface. Jupiter's moon Europa appears to contain a global ocean beneath a shell of ice. Saturn's moon Enceladus releases plumes of water vapor and icy particles from fractures near its south pole. Some of those particles contain salts, organic compounds, and other signs of interaction between liquid water and rock. These moons are not distant points beyond observation. Spacecraft have passed near them. Instruments have sampled their environments. Their hidden oceans are now serious targets in the search for habitable places. Water also appears beyond the solar system. Astronomers study the light passing through or emerging from exoplanet atmospheres. Molecules absorb certain wavelengths, leaving patterns that can reveal atmospheric composition. Water vapor has been detected in the atmospheres of several distant worlds. Many of these planets are too hot, too large, or too hostile for life resembling Earth's organisms. The importance lies in the larger pattern. Water does not seem to be a local accident. The chemistry that produces it is woven into the universe. Hydrogen is abundant, oxygen is made by stars. When conditions allow, the two elements combine. A molecule that fills Earth's oceans also forms in the darkness between suns. The question of alien life, therefore, does not begin with imaginary visitors or mysterious machines. It begins with chemistry. Do the same ingredients gather elsewhere? They do. Can organic molecules form without life? They can. Can water exist on planets, moons, comets, and within interstellar clouds? It can. Can planetary systems provide long periods of relative stability? Many appear capable of doing so. The pieces are widespread. What remains unknown is how often those pieces arrange themselves into living systems. On Earth, the transition from chemistry to biology happens very early in the planet's history. Earth forms roughly 4.5 billion years ago. The oldest widely accepted evidence of life appears within the first billion years, although the exact timing remains under study. This early appearance is intriguing. Once the planet cools, oceans form, and conditions become suitable, life seems to emerge without waiting through most of Earth's history. There is only one known example, so no reliable probability can be calculated. Perhaps life begins easily when conditions are right. Perhaps Earth benefits from an extraordinarily unlikely sequence of events. The evidence does not yet decide between these possibilities. Still, the speed of life's arrival keeps the question open. Earth does not remain lifeless for billions of quiet years before biology finally begins. Microbial life appears while the planet is still young. For most of Earth's history, life remains microscopic. There are no animals, trees, or complex ecosystems. Yet microbes transform the planet. Some learn to use sunlight. Some release oxygen. Some survive without oxygen at all. Life spreads into oceans, sediments, hot springs, rocks, and eventually the atmosphere. Its earliest forms are simple, but persistent. This suggests that the first great step may not require intelligence, language, or complex bodies. It may require only chemistry, energy, liquid water, and time. Those conditions are not unique to Earth. Energy is available throughout planetary systems. Starlight warms surfaces and atmospheres. Radioactive elements heat planetary interiors. Gravitational forces flex moons and generate friction. Chemical reactions near rocks can release energy without any sunlight. On Earth, some ecosystems thrive around hydrothermal vents deep in the ocean. Sunlight never reaches these places. Instead, microorganisms use chemical energy from minerals and heated water. Entire communities survive through chemosynthesis rather than photosynthesis. This expands the range of environments where life might begin or endure. A world does not always need a bright surface beneath a gentle sun. It may have a dark ocean beneath ice. It may contain warm water moving through rock. It may offer chemical energy for billions of years. Europa and Enceladus become especially interesting for this reason. Their surfaces are cold, but their interiors may remain active. Gravity from nearby giant planets repeatedly stretches and compresses them. This tidal flexing creates heat. Beneath the ice, liquid water may touch a rocky seafloor. If that interaction releases useful chemicals, the basic setting could resemble parts of Earth's deep ocean. No organism has been found there. Yet such places show that habitability can hide beneath appearances. A frozen surface may shelter a quiet ocean. A distant moon may contain more liquid water than Earth. A world without warm sunlight may still have energy, chemistry, and time. The search for life has therefore changed. It no longer focuses only on planets that look exactly like Earth. Scientists now examine many kinds of environments. Some are dry, some are frozen, some are buried beneath kilometers of ice. Some orbit faint red stars. Some drift within systems very different from the solar system. Earth remains the only confirmed living world. But Earth's chemistry is no longer isolated. Its elements fill the galaxy. Its water appears in ancient clouds and distant atmospheres. Its organic molecules form inside meteorites and between the stars. The universe seems able to prepare the ingredients again and again. Whether those ingredients awaken elsewhere remains unknown. Yet in every cloud of carbon, every frozen grain of water, and every young planet circling a newborn star, the same quiet possibility returns. Long before life opens its eyes, the cosmos is already setting the table. For most of human history, the planets of the solar system are the only worlds known to exist. Mercury moves close to the Sun. Venus glows behind its pale clouds. Mars crosses the night with a soft reddish color. Jupiter and Saturn travel more slowly, accompanied by their many moons. Beyond them lie Uranus, Neptune, and a wide darkness filled with smaller frozen bodies. These worlds once seemed like a complete family. The Sun is their center, and perhaps no other star possesses anything similar. Today, that idea has quietly faded. Planets are not unusual companions of stars. They appear to be one of the natural results of star formation. When a young star is born, it often forms inside a rotating cloud of gas and dust. Most of the material gathers at the center and becomes the star. The remaining material spreads into a broad, flattened disk. Inside that disk, particles begin to meet. Dust grains touch and cling together. Small clusters become larger ones. Pebbles gather into rocky bodies. Some of these objects collide. Others merge gently over millions of years. Eventually, planets emerge. This process is not special to the Sun. Astronomers observe young stars surrounded by disks throughout the Milky Way. Some disks contain rings, gaps, and spiral patterns. These structures may be shaped by planets that are still forming within them. The galaxy appears to contain countless planetary construction sites. New worlds are assembling while their stars are still young. The first confirmed planets found around a Sun-like star are announced in 19. They orbit a star called 51 Pegasi, located about 50 light-years away. The first planet detected there receives the name 51 Pegasi b. It is unlike anything expected. The planet is a gas giant. Its mass is comparable to Jupiter's, yet it circles extremely close to its star. One orbit takes only a little more than 4 Earth days. A world so large seems as though it should form far from its sun, where colder material is more abundant. Instead, 51 Pegasi b rests near the heat of its star. The discovery reveals that other planetary systems do not need to resemble the solar system. Nature follows many arrangements. Some planets orbit close to their stars. Others travel along stretched paths. Some systems contain several small worlds packed into a region narrower than Mercury's orbit. The galaxy is not simply repeating Earth, Mars, Jupiter, and Saturn around every sun. It is experimenting with a vast variety of structures. The detection of 51 Pegasi b begins a new age of astronomy. A planet near another star is called an exoplanet. These worlds are usually too faint to see directly because their stars are overwhelmingly bright. Astronomers therefore learn to find them through their effects. One common method observes a star's motion. A planet does not orbit a perfectly motionless star. Both objects move around a shared center of gravity. A large planet can gently pull its star back and forth. This movement changes the star's light by a tiny amount. When the star moves toward Earth, its light shifts slightly toward shorter wavelengths. The change is small, but sensitive instruments can measure it. The star seems to sway in response to an unseen companion. From that motion, astronomers can estimate the planet's orbital period and minimum mass. A distant world becomes visible through the rhythm it creates in starlight. Another method watches for shadows. If a planet's orbit passes between its star and Earth, the planet blocks a small portion of the star's light. The star becomes slightly dimmer. This event is called a transit. For a large planet crossing a small star, the drop in brightness may be easy to detect. For a small rocky planet, the change can be very delicate. The star brightens again when the planet completes its passage. If the dimming repeats at regular intervals, it can reveal the presence of an orbiting world. The time between transits gives the length of the planet's year. The amount of light blocked provides an estimate of its size. When transit measurements are combined with the star's motion, scientists can estimate both the planet's mass and radius. Those values reveal its average density. A dense world may be mostly rock and metal. A less dense planet may contain thick layers of gas or large amounts of water and ice. A barely visible shadow can therefore reveal the broad character of a planet many light-years away. One of the most successful planet-hunting observatories is the Kepler Space Telescope. Kepler launches in 2009 and spends years watching a crowded region of the sky. It repeatedly measures the brightness of more than 100,000 stars, searching for regular dips caused by transiting planets. The telescope does not travel to those systems. It simply watches. Night after night, it gathers light. From those tiny changes, a remarkable picture emerges. Planets are common. Many stars possess them. Some stars have one known planet. Others belong to systems containing several worlds. Kepler discovers planets larger than Jupiter and planets smaller than Earth. It finds worlds with extremely short years and others traveling much farther from their stars. It also reveals a type of planet missing from the solar system. These worlds are often called super-Earths or sub-Neptunes. A super-Earth is generally larger than Earth, but smaller than Neptune. The name describes size or mass, not habitability. A super-Earth may be a rocky planet, a water-rich world, or a small gas planet with a deep atmosphere. Sub-Neptunes usually possess thick envelopes of hydrogen and helium. Some may contain vast layers of water beneath their gases. These planets appear frequently in other systems, yet the solar system contains no world between Earth and Neptune in size. This absence is a gentle reminder that the local neighborhood is only one arrangement among many. The galaxy contains common types of planets that never form here, or that disappear early in the solar system's history. The search continues with the Transiting Exoplanet Survey Satellite, usually called TESS. Unlike Kepler, which concentrates on one distant region, TESS examines broad areas across nearly the entire sky. It looks especially for planets around stars that are relatively nearby and bright. Nearby systems are valuable because they are easier to study in greater detail. When a planet transits a bright star, larger telescopes can examine the starlight passing through its atmosphere. Each gas absorbs particular wavelengths. The atmosphere leaves a chemical fingerprint. In this way, astronomers may detect water vapor, carbon dioxide, methane, sodium, or other molecules. The measurement is extraordinarily delicate. The planet may be a small dark circle crossing a star much larger than itself. Only a thin ring of atmosphere filters the light. Yet within that faint signal rests information about the air of another world. A planet does not need to be visited for its sky to be studied. Its atmosphere writes a quiet signature across the spectrum of its star. The James Webb Space Telescope expands this work. Its large mirror and infrared instruments allow it to examine some exoplanet atmospheres with unusual sensitivity. Webb studies hot gas giants, warm Neptunes, and smaller rocky worlds orbiting relatively cool stars. Many of the easiest planets to examine are not likely homes for familiar life. Some are intensely heated. Some contain crushing atmospheres. Others orbit active stars that send strong radiation into space. These planets remain valuable. They teach astronomers how atmospheres form, change, and sometimes disappear. They reveal how clouds affect observations. They show how gases circulate between the hot and cool sides of tidally locked worlds. Every atmosphere becomes part of a larger library. Eventually, that library may help distinguish ordinary planetary chemistry from chemistry influenced by life. One especially important idea is the habitable zone. This is the range around a star where temperatures might allow liquid water to exist on a planet's surface. The concept depends on many details. A planet too close to its star may become extremely hot. Its oceans may evaporate. Water vapor may rise into the upper atmosphere and escape into space. A planet too far away may become frozen. Between these regions lies a zone where liquid water could remain stable, provided the planet has a suitable atmosphere. The habitable zone is sometimes called the Goldilocks zone because conditions may be neither too warm nor too cold. Yet the phrase can make the idea sound simpler than it is. Distance alone does not determine habitability. Venus lies near the inner region of the Sun's habitable zone, but its thick carbon dioxide atmosphere traps immense heat. The surface is far hotter than an ordinary oven. Mars lies near the outer region. It once contains rivers and lakes, but its atmosphere becomes thin. Today, stable liquid water cannot remain across most of its surface. Earth stays habitable because many conditions work together. Its distance from the Sun matters. So does its atmosphere. Its mass helps it retain gases. Its magnetic field offers some protection from charged particles. Its oceans transport heat. Its rocky interior cycles carbon over geological time. The Moon stabilizes Earth's rotation to some degree. Jupiter may influence the movement of smaller bodies, though its role is complex. The Sun itself remains relatively stable over long periods. Habitability is not one condition. It is a conversation between a planet, its atmosphere, its star, and time. Even so, the habitable zone offers a useful starting point. Astronomers have found many planets traveling within the temperate regions of their stars. One famous system surrounds a small star called TRAPPIST-1. The star lies about 40 light-years away. It is an ultra-cool red dwarf, much smaller and cooler than the Sun. 7 roughly Earth-sized planets orbit it. Their paths are so compact that all 7 would fit well within the orbit of Mercury if placed in the solar system. Several receive amounts of starlight that could permit moderate temperatures under suitable atmospheric conditions. The planets are named TRAPPIST-1, B through TRAPPIST-1H. They move in a delicate gravitational pattern. Their orbital periods are linked through resonances, with each planet influencing its neighbors. If seen from one of these worlds, nearby planets might appear as bright disks in the sky, sometimes larger than the Moon appears from Earth. The system offers no confirmed sign of life. Some planets may have lost their atmospheres, others may possess air too thin, thick, or chemically unfamiliar for life as known on Earth. Yet TRAPPIST-1 demonstrates how many rocky worlds can gather around a single small star. One quiet red sun can carry an entire family of planets. Red dwarfs are especially important because they are the most common stars in the Milky Way. They are smaller, cooler, and dimmer than the Sun. Because they produce less energy, their habitable zones rest close to them. A planet in such a zone may complete an orbit in days or weeks rather than one Earth year. The close orbit makes the planet easier to detect. It passes in front of its star more frequently, producing repeated transits. However, red dwarfs also create challenges. Young red dwarfs can be active. They may release strong flares and streams of charged particles. A nearby planet's atmosphere could be altered or gradually stripped away. Many close planets also become tidally locked. The same side may always face the star, while the opposite side remains in darkness. At first, such a world may seem divided between heat and ice. Atmospheres and oceans can transport energy, however. Winds may carry warmth toward the night side. Clouds may reflect light from the day side. A broad region near the boundary between light and darkness might remain mild. Computer models explore these possibilities. The results depend on atmospheric pressure, composition, oceans, continents, clouds, and the strength of the star's radiation. Tidal locking does not automatically prevent habitability. It simply creates a different kind of climate. One hemisphere rests beneath a permanent sun. The other looks into an endless night. Between them lies a ring of eternal evening. The diversity of exoplanets extends far beyond temperate rocky worlds. Some planets orbit 2 stars. From their surfaces, 2 suns might rise and set across the sky. Their paths are more complicated than Earth's orbit, yet such systems can remain stable. Other planets travel alone through the galaxy. These rogue planets do not orbit stars. They may be thrown from young planetary systems through gravitational encounters. Without direct starlight, their surfaces are likely cold. Yet a massive rogue planet could retain internal heat. A thick atmosphere might slow the loss of warmth. Some wandering worlds may even possess hidden oceans beneath ice. They move through the spaces between stars, accompanied only by their moons. There are also planets orbiting dead stars. Pulsars are the dense remnants of massive stars. They rotate rapidly and release beams of radiation. The first confirmed exoplanets are actually found around a pulsar in the early 90s. Their discovery is deeply surprising. The star that once occupied the system ends in a supernova. Any original planets may be destroyed or transformed. The existing worlds may form later from material surrounding the stellar remnant. Planet formation can therefore continue in environments very different from the quiet youth of the Sun. Worlds gather around stars that are young, old, small, bright, or already changed beyond recognition. The universe appears remarkably skilled at making planets. Some systems are tightly ordered. Kepler 90 contains many known planets, all orbiting closer to their star than Earth orbits the Sun. Other systems are widely spaced. Some planets move in nearly circular paths. Others follow elongated orbits that bring dramatic seasonal changes. Some worlds are rich in iron. Some may contain deep global oceans. Some possess atmospheres so light and expanded that they resemble clouds more than solid planets. There are hot Jupiters with winds racing across their skies. There are lava worlds whose surfaces may contain seas of molten rock. There are cold giants far from their stars. There may be planets with no exposed land, planets covered in haze, and planets beneath atmospheres, unlike anything familiar on Earth. This variety changes the meaning of the search for life. A living world may not look like a second Earth. Its oceans might lie beneath ice. Its air might contain gases uncommon here. Its organisms might depend on dim red sunlight or chemical energy from rock. Even familiar biology on Earth displays remarkable flexibility. Microorganisms survive in acidic lakes, deep stone, polar ice, hot springs, and the dark ocean floor. Some endure high radiation, some remain inactive through long dry periods, and become active when water returns. These organisms do not prove that life exists on extreme exoplanets. They reveal that life can occupy a wider range of environments than once imagined. The definition of a suitable world continues to expand. Astronomers now search not only for planets in habitable zones, but also for signs of stable atmospheres, liquid water, active geology, and useful chemical energy. They study stars as carefully as planets. A calm star may allow an atmosphere to survive. A long-lived star may provide billions of years for evolution. The star's ultraviolet light may help create some molecules while breaking apart others. The relationship is delicate. Too little energy can slow chemistry. Too much can remove an atmosphere. Between these extremes, a world may remain steady for immense periods. Time may be one of the most important ingredients. Simple life appears early on Earth, but complex organisms take billions of years to develop. Intelligence capable of building instruments and sending signals appears only very recently in geological history. A planet may be habitable without being inhabited. It may be inhabited only by microbes. It may support complex ecosystems that never produce technology. Or it may contain a civilization that exists during a period completely separate from humanity's own brief moment. The large number of planets makes every possibility worth considering. Even if life begins on only a small fraction of suitable worlds, the Milky Way contains enough stars for that fraction to matter. Yet numbers alone are not proof. A forest may contain countless leaves without containing a second Earth. A galaxy may hold countless planets while biology remains rare. The exoplanet discoveries do not settle the question. They remove one of the oldest reasons for assuming Earth is alone. There is no shortage of worlds. The universe is not mostly stars surrounded by emptiness. It is filled with systems, orbits, moons, rings, asteroids, and planets. The night sky hides landscapes beyond counting. Some may have clouds, some may have rain, some may contain oceans illuminated by unfamiliar suns. The nearest living world, if one exists, might orbit a star too faint to notice without a telescope. Its organisms may be microscopic, resting beneath soil or water. They may never see the stars above them. Farther away, other planets may have followed entirely different histories. Their continents may gather into unfamiliar shapes. Their skies may glow beneath two suns. Their seas may rise and fall under the pull of several moons. None of these images is confirmed. They are possibilities created by real worlds and real physical laws. The central fact remains calm and clear. Planets form naturally. They form often. They form in astonishing variety. Earth is no longer the only known stage on which life could appear. It is one world among a vast population. Across the Milky Way, stars carry planets through the dark. Some circle close to red dwarfs. Some follow broad paths around stars like the Sun. Some drift without a star at all. Most will remain silent and lifeless. Others may contain chemistry that is slowly becoming more complex. And somewhere, perhaps beneath a pale atmosphere or a quiet ocean, the same transition that once occurred on Earth may have happened again. The galaxy has provided the worlds. The question is whether any of them have learned to live. For much of scientific history, life appears to need a narrow and gentle home. It seems to belong near sunlight, fresh water, moderate temperatures, and breathable air. Plants grow beneath the sun. Animals move through forests, oceans, and open landscapes. Human beings live within a thin layer of atmosphere near Earth's surface. This familiar view creates an equally familiar assumption. If another world is too cold, too hot, too dark, too salty, or too dry, then life cannot exist there. Earth slowly teaches a different lesson. Living organisms occupy environments once considered almost completely uninhabitable. They live in boiling water. They remain active inside acidic pools. They endure beneath thick Antarctic ice. They survive in deep rock, far from sunlight and the open air. Some organisms draw energy from iron, sulfur, hydrogen, or methane. Others remain inactive for years, waiting quietly for water to return. Life does not require comfort. It requires an environment where chemistry can continue. This discovery greatly expands the search for life beyond Earth. A distant planet does not need forests or blue oceans visible from space. A moon does not need warm sunlight across its surface. A world may look frozen, dry, or empty, while biology persists in a sheltered place below. The first clues come from organisms now called extremophiles. The word describes life that thrives under conditions considered extreme from a human perspective. Some extremophiles prefer high temperatures, others favor intense cold, strong acidity, high pressure, concentrated salt, or environments with very little water. Many belong to the microbial world. They are bacteria or archaea, organisms so small that millions may gather in a single drop of water. Their simplicity is part of their strength. They do not need lungs, leaves, bones, or nervous systems. A single cell can perform every process required for survival. It gathers energy, it repairs itself, it grows, and when conditions allow, it divides. Among the most remarkable environments on Earth are hydrothermal vents on the deep ocean floor. These vents form where seawater moves through cracks in the crust. The water is heated by hot rock below the seabed. It reacts with minerals and rises again, carrying dissolved chemicals. When the heated water meets the cold ocean, minerals collect into tall structures. Some resemble dark chimneys, others form pale towers and delicate terraces. Sunlight never reaches these places. The ocean above may be several kilometers deep. The pressure is immense. The surrounding water is close to freezing, while fluid emerging from some vents can be hundreds of degrees warmer. Yet the vents support rich communities. Microorganisms live around the openings and use chemical energy released by reactions involving hydrogen sulfide, hydrogen, methane, and other substances. This process is called chemosynthesis. It performs a role similar to photosynthesis, but it does not depend on light. Plants near Earth's surface use sunlight to build energy-rich molecules. Vent microbes use chemical reactions instead. Other organisms depend on these microbes. Tube worms grow near some vents. Their bodies contain bacteria that provide nourishment. Crabs, shrimp, mussels, and other animals gather around the warm chemical flow. An ecosystem develops in permanent darkness. The discovery of these communities changes the idea of habitability. Before they are found, sunlight seems almost inseparable from life. Afterward, it becomes clear that a world can support biology without receiving light at its surface. Energy may come from within. This possibility matters for the frozen moons of the outer solar system. Europa orbits Jupiter beneath a bright shell of ice. Enceladus circles Saturn and releases icy plumes into space. Both moons appear to contain oceans below their surfaces. If water interacts with warm rock on their seafloors, chemical reactions may provide energy. No one knows whether hydrothermal systems exist there exactly as they do on Earth. Yet the basic ingredients are plausible. There may be liquid water, there may be rock, there may be internal heat. There may be chemical differences that life could use. A dark ocean beneath ice is no longer automatically considered lifeless. Earth has shown that darkness can be filled with metabolism. Some of the organisms living near hydrothermal systems prefer extraordinary heat. These microbes are called thermophiles when they thrive at high temperatures. Those that prefer even hotter environments are sometimes called hyperthermophiles. Many belong to the archaea. Archaea can resemble bacteria in size and shape, but they form a distinct domain of life. Their cell membranes and molecular machinery contain important differences. Some species grow best at temperatures above the boiling point of water at Earth's surface. Deep beneath the ocean, high pressure keeps water liquid even at these temperatures. The proteins inside these organisms remain stable where ordinary proteins would lose their shape. Their cell membranes are also specially adapted. Instead of being damaged by heat, their chemistry allows them to continue functioning. Life does not merely endure the warmth, it prefers it. Hot springs provide another home for thermophiles. In places such as Yellowstone National Park, heated water rises through volcanic ground. Pools and streams take on vivid colors. Some colors come from minerals. Others come from communities of microorganisms. Different microbes gather at different temperatures. Bands of color can form where the water gradually cools. Each band represents a narrow chemical neighborhood. One species grows in hotter water. Another settles farther away. The landscape becomes a living map of temperature. Hot springs may resemble environments that existed on the young Earth. They provide water, minerals, and a steady flow of energy. Some theories about life's origin place important early reactions in similar settings. Other theories favor the deep ocean or shallow pools exposed to repeated cycles of wetting and drying. The exact birthplace of life remains uncertain. Yet extremophiles reveal that biology can adapt to environments that seem far removed from ordinary surface conditions. Heat is only one limit. At the opposite end lies the cold. Polar regions remain frozen for long periods. Water becomes locked inside ice. Chemical reactions slow. Nutrients may be scarce. Still, microorganisms survive. Some remain active in thin films of liquid water between ice crystals. Salts can lower the freezing point, allowing small pockets of water to remain unfrozen. Certain microbes produce proteins that help prevent damaging ice crystals from growing inside their cells. Others adjust the fats in their membranes, so those membranes remain flexible in cold conditions. These organisms are called psychrophiles. They live in polar oceans, glaciers, snowfields, and frozen ground. Some exist beneath Antarctic ice, where lakes remain sealed from the surface for immense periods. The ice above creates pressure, while heat from the ground and insulation from the thick ice help maintain liquid water below. These hidden lakes are difficult to study without introducing contamination. Even so, their existence broadens the range of possible habitats. A surface can remain frozen while liquid water persists underneath. Mars may contain salty liquid water in brief or localized conditions beneath the ground, although the details remain uncertain. Icy moons almost certainly preserve larger hidden reservoirs. The lesson from Earth is not that these worlds contain life. The lesson is that ice does not end the question. It may protect what lies below. Ice can shield water from radiation. It can slow evaporation. It can preserve stable conditions for long periods. Above, the surface may be quiet and pale. Below, chemistry may continue in darkness. Some organisms survive not only cold, but also long periods without liquid water. Deserts offer a different challenge. In the Atacama Desert of South America, certain regions receive extremely little rainfall. The soil can remain dry for years. Ultraviolet radiation is strong. Organic material is scarce. Salts collect in the ground. The environment has become an important testing site for instruments designed to search for life on Mars. Yet even here, microbial communities exist. Some organisms live within or beneath rocks, where they receive partial protection from sunlight and where tiny amounts of moisture collect. Others become active during rare periods of increased humidity. Life slows. It waits. A small change in the environment allows metabolism to begin again. This ability appears throughout the natural world. Spores can preserve bacteria through long periods of dryness. Seeds remain inactive until water returns. Microscopic animals called tardigrades can enter a state in which their metabolism becomes extremely low. Tardigrades are often called water bears because of their rounded bodies and slow movements. They live in moss, soil, freshwater, and marine environments. When conditions become dry, some species contract into a protected form. Their bodies lose much of their water. Special molecules help protect cells and proteins. In this state, they may endure conditions that would normally stop biological activity. Tardigrades are complex animals, not microbes. Their survival abilities are impressive, but they should not be mistaken for evidence that animals could live openly on another planet. They generally need suitable conditions to become active again. Their importance lies in what they demonstrate. Biology can pause. An organism may survive a difficult interval without actively growing. On a world with changing seasons, repeated freezing, or occasional water, dormancy could be a powerful strategy. Life may spend most of its time waiting. Salt creates another kind of extreme environment. High concentrations of salt pull water away from cells. This can damage ordinary organisms and interrupt their chemistry. Halophiles are adapted to salty conditions. Some archaea thrive in lakes where salt concentrations are far higher than those of the ocean. Their cells maintain a chemical balance that prevents water loss. Certain halophiles produce pigments that make bodies of water appear red, pink, or purple. These pigments can help capture light or protect cells from radiation. Salt-rich environments matter in the search beyond Earth, because salty water can remain liquid at lower temperatures than pure water. Mars contains many salt deposits. Europa's ocean may include dissolved salts. Enceladus releases salty particles within its plumes. A cold environment with briny water may remain chemically active even when ordinary water would freeze. Salt can make life difficult. It can also keep water available. Acid provides another challenge. Most familiar organisms depend on cells that maintain a carefully controlled internal chemistry. Strongly acidic surroundings can disrupt proteins and membranes. Acidophiles live where the surrounding environment has a very low pH. Some occupy acidic hot springs. Others live in waters influenced by sulfur-rich minerals or mining activity. Their cell membranes limit the movement of hydrogen ions into the cell. Molecular pumps and repair systems help maintain a more stable interior. Some acidophiles gain energy by oxidizing iron or sulfur. They do not simply tolerate the environment. Their metabolism is built around it. At the opposite end, alkalophiles prefer strongly basic conditions. They live in alkaline lakes, soils, and industrial environments. Their cells face the challenge of gathering enough hydrogen ions to power essential processes. Again, biology finds a solution. Different organisms adapt to different chemical worlds. This flexibility is important because the oceans and atmospheres of other planets may not resemble those of Earth. A world does not need a neutral blue ocean to be considered interesting. Its lakes may be acidic. Its water may be rich in ammonia, salts, or dissolved minerals. Its air may contain gases that seem unusual from an earthly perspective. Life, if it begins there, may adapt to local chemistry rather than waiting for Earth-like conditions. Radiation once appears to set another firm boundary. Radiation can damage DNA. It breaks chemical bonds and creates reactive molecules within cells. Yet some organisms possess remarkable repair systems. The bacterium Deinococcus radiodurans is famous for surviving levels of ionizing radiation far beyond those tolerated by humans. Its DNA may break into many fragments. Instead of allowing the damage to become permanent, the cell repairs the pieces with unusual efficiency. The bacterium does not evolve in a nuclear facility. Its abilities may originally arise as an adaptation to drying. Severe dehydration can damage DNA in ways that resemble radiation damage. A strong repair system useful in dry environments also provides resistance to radiation. This is a common pattern in evolution. An adaptation serving one purpose may help an organism survive another challenge. Radiation-resistant microbes matter because the surfaces of Mars and some icy moons receive much more radiation than Earth's surface. Earth is protected by a thick atmosphere and a global magnetic field. Mars has a thin atmosphere and no strong global magnetic shield. Jupiter's radiation environment is especially intense around Europa. Surface life would face serious difficulty. Yet rock, soil, water, and ice provide protection. Even a modest depth can reduce radiation exposure. A world may have an inhospitable surface, while preserving a more stable habitat underground. The search, therefore, often looks below. Life beneath Earth's surface is one of the most important biological discoveries of recent decades. Microorganisms exist deep within rock, sediments, mines, and the seafloor. Together, these environments form part of the deep biosphere. Some organisms live hundreds of meters or even kilometers beneath the surface. They receive no sunlight. Nutrients arrive slowly. Their metabolism may proceed at an extremely low rate. A cell near the surface may divide quickly when food is abundant. A cell deep underground may take years or far longer to reproduce. Its existence follows a quieter rhythm. Energy can come from chemical reactions between water and rock. In one process, water reacts with certain minerals and produces hydrogen. Microorganisms can use this hydrogen as an energy source. Other microbes consume methane, sulfur compounds, or iron. Entire ecosystems may remain disconnected from sunlight for long periods. This deep life changes estimates of Earth's living volume. The planet's biosphere is not only a thin green layer across the surface, it extends downward into stone. The organisms there are mostly invisible, but their combined presence may be enormous. This has direct importance for Mars. The Martian surface is cold, dry, and exposed to radiation. Ancient Mars is very different. Rivers flow, lakes gather in craters, deltas form. The atmosphere is thicker. As the planet changes, surface conditions become less favorable. If life ever begins there, it may retreat underground. Water could remain within buried ice, mineral layers, or small briny regions. Rock could provide protection. Chemical reactions might provide energy. The most promising Martian organisms may not be waiting openly beside a dry river valley. They may exist far below, moving through microscopic spaces between grains of stone. This possibility is difficult to test. Landers and rovers usually examine the surface or drill only a short distance. Reaching deep protected layers requires more complex missions. Even so, Earth's deep biosphere keeps the possibility scientifically reasonable. Where light ends, life may continue. Another surprising lesson comes from organisms living inside rocks. In deserts and polar regions, some microbes occupy pores beneath a rock's surface. The stone provides shade, retains small amounts of moisture, and reduces exposure to wind and radiation. A bare landscape may appear lifeless from a distance. Closer examination reveals thin green or dark layers within the rock. These communities are called endoliths. The word means life within stone. Endoliths may grow slowly because light and nutrients are limited. Yet the rock creates a small protected world. Similar habitats could exist on Mars. Transparent or partly translucent minerals might allow a little light to enter while offering shelter from surface radiation. No Martian endolith has been found. The comparison simply shows how easily life can remain hidden. A planet can look empty at the scale of mountains while containing organisms in individual rocks. Extremophiles also change the way scientists think about atmospheres. Many organisms on Earth do not need oxygen. In fact, early life evolves before oxygen becomes abundant in the atmosphere. Some microbes live only where oxygen is absent. They use other molecules during metabolism. Methanogens, for example, are archaea that produce methane. They often live in oxygen-free environments such as sediments, wetlands, animal digestive systems, and deep underground habitats. Some use hydrogen to convert carbon dioxide into methane. These organisms are ancient in their basic metabolism. They demonstrate that oxygen is not required for life. A planet may be alive while lacking a breathable atmosphere. For much of Earth's history, an observer from far away would not detect forests, animals, or large amounts of oxygen. The planet would still contain life. This means the search for inhabited worlds must consider many possible chemical signatures. Oxygen may be important, especially when it appears alongside gases that should react with it. Methane may also be significant in the right context, but each gas can be produced without biology. Volcanoes, water-rock reactions, sunlight, and atmospheric chemistry can create misleading signals. No single molecule is likely to provide effortless certainty. Scientists instead search for combinations. They study the planet's temperature, star, geology, atmosphere, and chemical balance. A biosignature is strongest when biological activity provides the most convincing explanation for several observations together. Earth itself offers an example. Oxygen and methane coexist in the atmosphere. These gases react and should gradually remove one another. Their continued presence means they are being replenished. Much of Earth's oxygen comes from photosynthetic life. Much of its methane is also connected to biological activity. Though geological sources exist, seen from far away, this chemical imbalance could suggest an active biosphere. Yet even Earth would not always be easy to identify. Clouds hide the surface. Atmospheric signals change over geological time. Life may remain microbial for billions of years. A distant observer might examine Earth during an early period and miss its biology entirely. The absence of an obvious signal does not always mean the absence of life. It may mean the life is small, buried, quiet, or chemically subtle. This is perhaps the most important lesson from extremophiles. Life can be difficult to notice. A hydrothermal vent ecosystem leaves little sign at the ocean's surface. Microbes inside rocks do not change the visible landscape dramatically. Organisms deep underground may never interact with the atmosphere. An inhabited world may not announce itself across space. It may simply continue. Cells may divide beneath ice. Microbes may gather around mineral-rich water. Thin films of life may rest inside stone. The planet may appear silent, while biology fills hidden spaces. Extremophiles are sometimes described as creatures that survive the impossible. A calmer and more accurate view is that the environments are only impossible for organisms adapted to somewhere else. A deep-sea microbe is not struggling to imitate a surface animal. It belongs to its environment. Its enzymes, membranes, metabolism, and structure reflect the conditions around it. Likewise, alien life would not need to endure an alien world. That world would be its home. A cold ocean beneath an icy moon may seem remote from human life. To an organism that begins there, the darkness and pressure would be ordinary. A planet orbiting a red dwarf may appear unusual from Earth, To its biology, a dim crimson sun may be the natural source of every day. The search for extraterrestrial life is therefore not a search for organisms that resemble humans. It is a search for matter that organizes itself, gathers energy, maintains its structure, and evolves. Earth shows that these abilities can appear in remarkable settings. Life is not infinitely adaptable. Every organism has limits. Too much heat destroys complex molecules. Too little energy can prevent metabolism. Some environments cannot maintain liquid solvents or stable chemistry. Extremophiles do not prove that life can exist anywhere. They show that the boundaries are wider than expected. Each newly discovered habitat moves the line. First, life is believed to require sunlight. Then communities are found around deep-sea vents. It is believed to need moderate temperatures. Then microbes are found in boiling springs and polar ice. It is believed to remain near the surface. Then cells are discovered deep inside Earth's crust. It is believed to require oxygen. Then entire ecosystems are found without it. The habitable universe grows larger without changing size. Places once ignored become possible homes. Frozen moons become ocean worlds. Dry planets become candidates for buried life. Dark wandering planets become less easy to dismiss. The evidence remains indirect. No extremophile on Earth proves that a single organism exists elsewhere. Yet these organisms remove many reasons for believing that extraterrestrial life is impossible. They show that biology is patient. It can slow almost to stillness. It can live without sunlight. It can use simple chemical reactions. It can shelter beneath ice and stone. It can repair damage and wait through long dry seasons. Most importantly, extremophiles reveal that life does not need a perfect planet. It needs a usable place. That place may be an ocean floor. It may be a warm crack in frozen rock. It may be a salty pocket beneath a desert. It may be a thin layer hidden inside a stone. Across the solar system and throughout the galaxy, there may be countless small environments like these. They would be difficult to see from Earth. They might leave no bright lights or radio signals. They might never build cities or look toward the stars. Yet even a single cell beyond Earth would transform humanity's understanding of life. It would show that biology is not a solitary event. It would mean that when matter, water, energy, and time meet under suitable conditions, life can begin more than once. For now, Earth provides the only confirmed example, but Earth's living boundaries continue to expand. In every boiling spring, every buried ocean current, and every quiet cell beneath the ground, the planet offers the same gentle message. Life may be far more difficult to exclude than it is to imagine. The search for life does not need to begin around a distant star. Several worlds within the solar system once possess, or may still possess, environments where biology could survive. They are close enough for spacecraft to photograph. Robotic explorers can touch their surfaces, measure their atmospheres, and sample material escaping from hidden oceans. None has provided confirmed evidence of an organism, yet each one weakens the old idea that Earth is the solar system's only potentially habitable place. Mars preserves ancient rivers and lakes. Europa appears to hold a global ocean beneath ice. Enceladus sends pieces of its hidden sea directly into space. Titan carries complex organic chemistry through its atmosphere and across its surface. These worlds are different from Earth. Their skies, temperatures, landscapes, and histories follow separate paths. But life does not require a second Earth in every detail. It requires useful chemistry, a source of energy, a stable environment, and enough time. The solar system may contain several places where those conditions once meet. Some may still meet today. Mars is the most familiar of these worlds. It shines as a quiet red point in Earth's night sky. Its surface is now cold and dry. Its atmosphere is thin and composed mostly of carbon dioxide. Liquid water cannot remain stable across most of the open ground for long. Radiation reaches the surface more easily than it does on Earth. Dust covers plains, valleys, volcanoes, and impact craters. At first glance, modern Mars appears to be a silent desert. Its rocks tell a much older story. Orbital spacecraft reveal networks of ancient valleys. Some stretch across enormous distances and branch like river systems on Earth. Channels cut through the landscape. Sediments collect in fan-shaped deposits. Minerals form that usually require water. Certain craters contain layers arranged like material settling gradually at the bottom of lakes. Mars has not always been the world seen today. Billions of years ago, water moves across its surface. Rain or melting ice may feed streams. Rivers enter craters and create lakes. Groundwater rises through rock. Hot springs may appear near volcanic regions. The ancient atmosphere is thicker, and parts of the planet remain warmer. The exact climate is still debated. Mars may not have been continuously warm. Long cold periods may have been interrupted by temporary melting. Even so, the physical evidence for ancient water is extensive. A dry valley is a memory preserved in stone. NASA's Curiosity rover explores Gale Crater, a large basin near the Martian equator. A mountain rises from the crater's center. Its layers preserve different periods of Martian history. Curiosity finds sedimentary rocks formed in an ancient lake environment. Mud settles slowly through water and becomes stone. Minerals within the rocks indicate that some of the water is not strongly acidic or overwhelmingly salty. The lake could have offered conditions suitable for microorganisms. It contains liquid water. It contains important chemical elements. It contains sources of energy that microbes might use. No fossil or cell is discovered there. The rover instead finds evidence that the environment itself was habitable. This distinction is essential. A house may be suitable for an occupant without proving that anyone lived inside it. Gale Crater appears to have been a suitable house for simple life. Whether biology ever entered remains unknown. Curiosity's observations show that Gale Crater once held a stable lake environment that could have supported microbial life. Curiosity also detects organic molecules preserved inside ancient Martian rocks. Organic compounds contain carbon and may participate in biological chemistry. They can be produced by organisms, but they can also form through non-living processes. Meteorites carry organic molecules. Volcanic activity and reactions involving water and rock can also create them. Their presence on Mars is therefore not proof of past life. It is still significant. Mars possesses some of the carbon chemistry needed for biology. The molecules survive within rocks for billions of years, despite the radiation and chemical activity at the surface. They show that the ancient environment is not chemically empty. The necessary pieces are present. Some may have formed on Mars. Others may have arrived through meteorite impacts. The planet receives the same broad cosmic ingredients that once reached the young Earth. Far from Gale Crater, another rover examines a different ancient lake. NASA's Perseverance rover lands within Jezero Crater. Long ago, a river flows through a valley and enters the crater. As the water slows, it releases sand, mud, and other material. The sediment builds a delta. River deltas on Earth are excellent places to preserve signs of life. They collect organic material from broad regions. Fine sediment can cover delicate structures and protect them from erosion. For this reason, Jezero becomes one of the most carefully chosen locations in the search for ancient Martian biology. Perseverance studies the delta's rocks. It examines their minerals and textures. It searches for organic compounds and patterns that may record the history of water. The rover also collects samples inside sealed tubes. These pieces of Martian rock may eventually allow far more detailed analysis than a rover can perform alone. Earth laboratories contain large instruments with extraordinary sensitivity. They can examine individual mineral grains. They can search for complex organic patterns. They can compare different chemical forms of the same element. Even then, the interpretation must remain careful. Geology can create shapes and chemical signals that resemble biology. A convincing discovery would likely require several independent clues pointing toward the same explanation. Jezero Crater preserves evidence of an ancient river, delta, and stable lake system, and Perseverance is collecting samples to study its geological and astrobiological history. Mars may also contain useful environments below its present surface. The upper ground is exposed to radiation. Oxidizing chemicals can break apart organic material. Water at the surface freezes, evaporates, or disappears into the soil. Deeper underground, the conditions may be calmer. Rock blocks radiation. Temperatures become more stable. Ice may remain protected. Small amounts of salty water could occasionally form where local conditions allow. Water moving through minerals can also release chemical energy. On Earth, deep microorganisms survive through similar reactions. If Mars ever develops life during its wetter youth, some descendants might retreat underground as the surface changes. They may enter protected cracks. They may survive within briny pockets. Their metabolism could become extremely slow. Such organisms would be difficult to find. A rover crossing the surface might pass above them without detecting anything. The most accessible evidence may instead be ancient material exposed by erosion or impact. Mars contains another mystery in the form of methane. Small amounts of methane have been reported in the Martian atmosphere by some observations. The measurements are difficult, and different instruments have not always produced matching results. Methane attracts attention because it does not remain indefinitely in an atmosphere. Sunlight and chemical reactions gradually destroy it. A continuing presence could mean that some process is replenishing it. On Earth, much methane is produced by living organisms. Microbes called methanogens release it while gathering energy in oxygen-free environments. But methane does not require life. Water can react with certain rocks and produce hydrogen. Further reactions can create methane. Volcanic or geothermal processes may also release it. Even if every Martian methane measurement is confirmed, the gas alone would not prove biology. Its value lies in the question it creates. What process is producing it? Where is it occurring? Does it emerge from underground? Does its abundance change with seasons or local geology? Mars repeatedly offers clues that are interesting but incomplete. The planet does not give a simple answer. It preserves a long scientific conversation inside its rocks. Perhaps life begins there, while rivers flow. Perhaps the chemistry approaches biology, but never crosses the boundary. Perhaps Mars remains sterile through its entire history. Each possibility is still open. The answer may wait inside carefully chosen samples. Beyond Mars, the search enters a colder region. Jupiter circles the Sun with a large family of moons. Among them is Europa, a world only slightly smaller than Earth's moon. Europa's surface is composed mostly of water ice. It is bright, smooth in some regions, and crossed by long reddish-brown lines. There are relatively few large impact craters. This suggests that the surface is geologically young. Older craters may be erased as the ice shifts and renews itself. The lines and broken regions hint that the shell has moved. Some areas resemble sheets of ice that crack, rotate, and freeze again. Beneath that changing surface lies one of the solar system's most promising environments. Evidence indicates that Europa contains a global ocean of salty liquid water. The ocean is hidden beneath an ice shell, whose exact thickness remains uncertain. Its existence is supported by several kinds of observation. The Galileo spacecraft measures changes in the magnetic environment around Europa. The best explanation is that Jupiter's powerful magnetic field induces electrical currents within a conductive layer inside the Moon. Salty liquid water is a strong candidate for that layer. Europa's fractured terrain also appears consistent with a shell moving above liquid water or softer ice. Surface materials may include salts originating from below. Together, these clues create a picture of an ocean world concealed beneath a pale crust. Europa may contain more liquid water than all of Earth's oceans combined. Its moon-sized body is smaller than Earth, but the hidden ocean may be very deep. On Earth, oceans cover the surface in a relatively thin layer. Europa's sea could extend for many kilometers beneath its ice. The water remains liquid because the Moon is heated from within. Europa travels around Jupiter along a slightly stretched orbit. The gravitational pulls of Jupiter and neighboring moons continually change. Europa is gently squeezed and stretched. This repeated flexing produces heat through friction. It is known as tidal heating. The same broad process keeps several moons of the outer solar system geologically active. On Europa, tidal energy may warm the ice and possibly the rocky interior. If the ocean reaches a rocky seafloor, water and minerals can interact. These reactions could supply chemical energy. On Earth, similar interactions support microorganisms around hydrothermal systems and within deep rock. Europa therefore may possess three major requirements associated with life. It has liquid water, it may have useful chemistry, it has a continuing source of energy. None of these proves that a cell exists there. But together, they make Europa more than a frozen object. It becomes a possible habitat. The surface of Europa is exposed to intense radiation from Jupiter's environment. Charged particles strike the ice and alter its chemistry. They can split water molecules and create reactive compounds. At the surface, this radiation would make survival difficult for familiar organisms. The same process may create chemical energy. If surface compounds move downward through cracks or slow circulation, they could reach the ocean. There, they might react with materials arriving from the rocky seafloor. A contrast between oxidized surface chemistry and reduced seafloor chemistry could provide energy for metabolism. Life on Earth often depends on chemical differences. A battery produces energy because its two sides are not in equilibrium. Cells also use controlled imbalances. They move electrons from one molecule to another. Europa may contain a planetary version of such a system. Chemistry created above and below could meet within the ocean. The ice between them may not be a perfect barrier. Europa's surface contains regions called chaos terrain. In these areas, blocks of ice appear broken, shifted, and partly surrounded by smoother material. Some models suggest warm ice or pockets of liquid water rise toward the surface. Other models describe complex motion within the shell. Whatever the exact mechanism, Europa is not simply a solid frozen sphere. Its outer layers appear dynamic. Material may travel between the surface and the deeper interior over geological time. This exchange would be important for habitability. Nutrients must move. Waste products must disperse. Energy-rich compounds must come into contact. A perfectly sealed and motionless ocean could gradually lose accessible resources. A changing ice shell may help keep the environment chemically active. Scientists have also studied possible signs of water vapor near Europa. Some observations suggest that material may occasionally escape above the surface. The evidence for active plumes has been difficult to confirm consistently. Europa does not display the obvious persistent fountains seen at Enceladus. Even so, water vapor and surface exchange remain important areas of study. A plume would offer a natural window into the ocean or shallow reservoirs. A spacecraft could fly through the material without drilling through the ice. The moon may release samples of itself into space. Saturn's moon Enceladus does exactly that. Enceladus is small. Its diameter is only about 500 kilometers. Its surface is bright because it is covered in clean water ice. For many years, such a small moon seems unlikely to remain active. A small body loses internal heat more quickly than a large planet. It should become frozen and quiet. The Cassini spacecraft discovers something entirely different. Near Enceladus's south pole, long fractures cross the surface. Water vapor, ice particles, and gases rise from these cracks in immense plumes. The material travels far above the moon. Some particles escape and contribute to one of Saturn's rings. Others fall back onto the surface like fine snow. Enceladus is continually releasing material from its interior. Cassini passes directly through the plumes. Its instruments sample the particles and gases. This creates one of the most extraordinary moments in planetary science. A spacecraft does not need to land. It does not need to drill. The hidden ocean sends material outward, and Cassini moves through it. The plume contains water vapor. It contains salts. It contains carbon dioxide, methane, and organic compounds. Tiny silica particles suggest that warm water may interact with rock at the ocean floor. Molecular hydrogen is also detected. On Earth, hydrogen released by water-rock reactions can serve as food for microorganisms. Certain microbes combine hydrogen with carbon dioxide and produce methane. This does not mean microbes are performing the same process on Enceladus. It means that a known source of chemical energy is available. The plume indicates that Enceladus possesses liquid water, organic chemistry, and potential chemical energy. Another important element appears inside salt-rich ice grains. Phosphorus is essential for all known life. It forms part of DNA and RNA. It helps build cell membranes. It is central to molecules that cells use to store and transfer energy. For years, scientists wonder whether phosphorus might be scarce in the oceans of icy moons. Analysis of Cassini data reveals phosphates within grains released by Enceladus. The discovery completes an important chemical inventory. Carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus are all connected to Earth's biology. Enceladus appears to provide these ingredients within or around its ocean. Again, ingredients are not organisms. A kitchen can contain flour, water, and heat without producing bread by itself. Yet the finding removes another possible obstacle. The ocean does not appear to be missing one of life's central elements. Organic chemistry within the plume is also more varied than first recognized. Cassini detects both simple and more complex carbon-bearing molecules. Later analyses of its stored data reveal additional compounds. Some participate in chemical pathways related to molecules important in terrestrial biology. They may arise through non-living reactions within the ocean, at the seafloor, or inside rising plume material. They do not provide a biological signature. They show that Enceladus contains an active chemical environment. The ocean is not merely cold water beneath ice. It appears to be a mixture of salts, gases, minerals, and carbon compounds. Energy flows through it. Water interacts with rock. Material travels upward and escapes through fractures. This movement makes Enceladus an unusually accessible place to search. A future spacecraft could sample many plume particles with instruments designed specifically for biology. It could examine organic structures in finer detail. It could search for patterns in amino acids or other molecules. It could measure whether some compounds display a preference for one molecular orientation. Life on Earth often produces highly organized chemical patterns that random processes do not easily create. A convincing result would need to rule out contamination and non-biological chemistry. Enceladus offers a rare opportunity to attempt that work without descending through kilometers of ice. The ocean rises to meet the spacecraft. Farther within Saturn's system lies Titan. Titan is larger than Mercury. It is the only moon in the solar system with a thick atmosphere. Its air is mostly nitrogen, like Earth's atmosphere. Though Titan contains almost no breathable oxygen, methane forms an important smaller component. High above the surface, sunlight and energetic particles break apart nitrogen and methane molecules. The fragments recombine into increasingly complex carbon compounds. A thick orange haze develops. Organic particles drift downward through the atmosphere. Titan experiences a slow rain of carbon-rich material. Its chemistry may resemble some processes that occur on the young Earth before life changes the atmosphere. The surface is extremely cold. Water ice behaves like solid rock. Liquid water cannot remain openly stable. Instead, methane and ethane form clouds, rain, rivers, lakes, and seas. Titan is the only world beyond Earth known to possess stable bodies of liquid on its surface. The liquids are not water, they are hydrocarbons. Near the poles, dark lakes fill depressions in the landscape. Channels flow into broad seas. Clouds gather and storms occasionally release methane rain. The cycle resembles Earth's water cycle in its shape. Liquid evaporates, clouds form, rain falls, rivers return material to lakes. The molecules are different, but the planetary rhythm is familiar. Titan's surface is an organic chemical laboratory. Carbon compounds from the atmosphere settle onto dunes and icy ground. Methane rain carries them through channels. Impacts or geological activity may occasionally bring liquid water into contact with this material. Even brief periods of melted water could allow complicated reactions. Titan may also hide a global water ocean beneath its icy crust. The surface and subsurface are therefore two very different possible environments. Above lies a cold landscape shaped by liquid methane. Below may lie a deep ocean of water mixed with salts or ammonia. Scientists consider whether either region could support some form of chemistry related to life. The underground ocean is more familiar because it contains water. The surface creates a more unusual question. Could an unfamiliar biology use liquid methane or ethane instead? No known life does this. Terrestrial cells depend on water's chemical properties. Water dissolves many substances, carries ions, and supports the folding of proteins. Methane behaves very differently. At Titan's temperatures, chemical reactions proceed slowly. Cell membranes and metabolism would need structures unlike those on Earth. The idea remains speculative. It is not evidence of methane-based organisms. Titan is important because it allows scientists to study how far prebiotic chemistry can progress without known life. Its atmosphere continually creates organic molecules. Its weather distributes them. Its surface stores them. It offers natural experiments that have continued for immense periods. The Huygens probe provides the first direct view from Titan's surface. It descends through the orange atmosphere in 2005. During its fall, it photographs branching channels and rounded terrain. It lands on a plain scattered with pieces of water ice that resemble stones. The ground is dim beneath the haze. The scene is unmistakably alien, yet shaped by processes familiar from Earth. Fluids have moved across the surface. Material has been eroded and carried. Atmospheric chemistry has connected sky and ground. Titan shows that worlds can resemble Earth in structure, while differing completely in substance. A river does not have to contain water. A rock does not have to be made of silicate. Rain can fall from a methane cloud. A coastline can form beneath a sky where the sun appears as a faint glow. These variations matter in the search for life. Habitability may come in more than one form. The solar system also contains other places of interest. Ceres, the largest object in the asteroid belt, contains water-rich minerals and bright salt deposits. Some evidence suggests that briny liquids exist or once exist beneath parts of its surface. Several moons of Jupiter and Saturn are believed to contain internal oceans. Ganymede, the largest moon in the solar system, likely possesses layers of water and ice deep below. Callisto may also hide an ocean. Neptune's moon Triton displays a young surface and active plumes, suggesting internal processes continue there. Even Pluto reveals a complex geological history during the New Horizons flyby. A region once imagined as a collection of dead frozen objects becomes a landscape of active worlds. Ice can move like rock. Rock can behave like a source of heat. Gravity can warm a moon. An ocean can survive far beyond the traditional habitable zone. This changes the meaning of distance from the sun. Earth receives enough sunlight to maintain surface oceans. Europa and Enceladus receive far less. Their possible habitability comes from tidal energy and insulation. Thick ice slows the escape of heat. Water remains liquid beneath the shell. A moon far outside the sun's comfortable zone may preserve an ocean longer than a small planet closer in. The habitable zone around a star is useful, but it does not contain every possible habitat. There are also habitable environments inside worlds. A surface may be frozen while its interior remains warm. A planet may lose its atmosphere while groundwater survives below. A moon may have no air at all, yet contain a sea protected beneath ice. The search expands from habitable planets to habitable places. This is a subtle but important change. An entire world does not need to be friendly to life. Only one stable environment may be enough. Earth demonstrates this on a smaller scale. The upper atmosphere, deep crust, ocean floor, and polar ice are not equally comfortable. Life occupies the parts it can use. An extraterrestrial biosphere may also be concentrated. Europa's ocean may be active near the seafloor and sparse elsewhere. Martian life may survive only in scattered underground pockets. Titan's most interesting chemistry may occur near impact sites where organics meet temporary liquid water. A living world can contain vast regions without life. It can still be alive. The solar system's nearby candidates also provide a way to test whether life begins independently. Mars, Europa, Enceladus, and Titan have separate histories. If organisms are discovered on one of them, their chemistry can be compared with Earth's biology. Perhaps they use DNA and familiar amino acids. That similarity might mean that life shares a common origin. Material can travel between planets inside rocks thrown upward by impacts. Microbes sheltered within a rock could, in principle, move from one world to another if they survive the journey. This idea is called panspermia. It does not explain the first origin of life. It describes how life might spread after beginning somewhere. Earth and Mars have exchanged rocks naturally. Martian meteorites are found on Earth. Large impacts on Mars eject fragments into space. Some eventually cross Earth's path and fall to the ground. The reverse journey is also physically possible. If ancient Earth and Mars share microorganisms through such transfers, life on both worlds might belong to one family. Europa and Enceladus are more isolated. Their oceans lie beneath ice, far from Earth. Life discovered there could represent a second origin. Its cells might use different genetic molecules. Its proteins might rely on unfamiliar building blocks. Its membranes may have structures never seen before. Even if the organisms are simple, their existence would answer one of science's greatest questions. Life can begin more than once. Two independent origins within one solar system would suggest that biology may be common across the galaxy. The absence of life would also teach something important. A world can possess water, energy, and organic chemistry without becoming alive. Perhaps the transition from chemistry to biology requires rare conditions. Perhaps some ingredient remains undiscovered. Perhaps time and stability matter more than the presence of water alone. Every result would deepen the understanding of life. For now, the nearby worlds remain unanswered questions. Mars holds ancient lake beds beneath red dust. Europa carries a dark ocean under fractured ice. Enceladus releases frozen pieces of its sea into the space around Saturn. Titan gathers organic material beneath an orange sky. None offers proof that humanity has company. Together, they show that Earth is not the solar system's only place where the possibility can be taken seriously. Water is present. Carbon chemistry is present. Energy is present. Stable environments may persist for millions or billions of years. The search is no longer aimed at a single unlikely destination. It moves through a collection of worlds. Some are warm only in the past. Some are warm only inside. Some contain oceans without sunlight. Some contain rain without water. Each one expands the imagination while keeping the science grounded. Perhaps every hidden ocean is sterile. Perhaps Mars never advances beyond organic chemistry. Perhaps Titan's molecules continue combining without ever becoming cells. But perhaps, in one sheltered environment, chemistry crosses the quiet boundary into life. A membrane closes around a set of molecules. Energy begins to flow through an organized system. Information starts to copy itself. Small variations appear. Selection begins. The first organism would not know that it is first. It would not look toward Earth. It would simply continue, dividing slowly in darkness. Somewhere beneath nearby ice or ancient stone, that process may have happened. The worlds are close enough to visit. Their materials are beginning to be measured. And for the first time in human history, the question of life beyond Earth is becoming something that instruments may answer. Life changes a planet. It alters the air. It transforms oceans, soils, and rocks. It moves elements through repeating cycles and releases gases that would not remain abundant without constant renewal. Earth is the clearest example. Seen from nearby, the planet displays forests, cities, oceans, and animals. Seen across interstellar distance, those details disappear. Earth becomes a tiny point of reflected light beside a much brighter star. Yet its atmosphere still carries information. Oxygen fills much of the air. Water vapor moves through clouds and weather systems. Carbon dioxide participates in climate and photosynthesis. Methane appears in small amounts and is continually replenished. Together, these gases create a chemical pattern shaped strongly by life. This pattern offers one of the most promising ways to search for biology on worlds too distant to visit. Scientists call a remotely detectable sign of life a biosignature. A biosignature may be a gas, a combination of gases, a surface pigment, a seasonal change, or another measurable feature produced by biological activity. No single biosignature is automatically conclusive. Nature is inventive. Volcanoes release gases. Sunlight breaks molecules apart and creates new ones. Water reacts with rock. Lightning, impacts, and atmospheric circulation can build complicated chemistry without biology. A convincing discovery must therefore depend on context. The planet's atmosphere matters. Its temperature matters. Its oceans, rocks, star, and geological history matter. A gas becomes meaningful only when the processes that produce and remove it are understood. The search is not simply for oxygen. It is for chemistry that appears difficult to maintain without life. This idea is sometimes described as atmospheric disequilibrium. Chemical systems naturally move toward balance. Reactive substances meet and transform into more stable combinations. If two gases strongly react with one another, they should not remain together for long unless some process continually replaces them. Earth's atmosphere contains several such imbalances. Oxygen is highly reactive. It combines with minerals. It supports combustion. It participates in reactions with many atmospheric compounds. Without photosynthetic organisms, much of Earth's free oxygen would gradually disappear. Methane also reacts with oxygen and is broken apart by atmospheric chemistry. Its typical lifetime in the atmosphere is short compared with the age of the planet. Yet methane continues to exist. It is constantly replaced by wetlands, microorganisms, agriculture, geological processes, and other sources. The simultaneous presence of oxygen and methane is therefore notable. The two gases should reduce one another over time. Their continued coexistence indicates active replenishment. On Earth, biology plays a major role in maintaining both. From far away, this imbalance could suggest a living planet. It would not provide immediate certainty. A distant world might produce oxygen through the breakdown of water or carbon dioxide. Methane might emerge from reactions between water and certain rocks. But if both gases appear in the right quantities, within a suitable climate, and alongside other supporting evidence, the biological explanation may become increasingly compelling. Life may be recognized not through one loud signal, but through several quiet clues that agree. Oxygen is often placed at the center of this search. On modern Earth, most atmospheric oxygen is produced by photosynthesis. Plants, algae, and cyanobacteria use sunlight to combine carbon dioxide and water into energy-rich molecules. Oxygen is released as a byproduct. This process seems ordinary because it surrounds human life. Green leaves open towards sunlight. Algae drift through oceans. Microscopic cyanobacteria form films across wet surfaces. Yet photosynthesis changes the entire planet. Early Earth contains very little free oxygen. The first organisms live in an atmosphere unlike the one breathed today. Some microbes eventually develop a form of photosynthesis that splits water molecules. The released oxygen initially reacts with iron and other materials. It does not immediately gather in the atmosphere. Oceans and rocks absorb much of it. Over long periods, these chemical sinks become less able to remove every new oxygen molecule. Oxygen begins to accumulate. This transition is known as the Great Oxidation Event. It occurs more than 2 billion years ago and permanently changes Earth's chemistry. The atmosphere becomes increasingly oxidizing. New forms of metabolism become possible. Complex organisms later use oxygen to extract large amounts of energy from food. A gas produced by tiny cells eventually helps prepare the planet for animals. Earth's history shows that life can modify a world on a global scale. It also reveals why oxygen must be interpreted cautiously. For much of Earth's inhabited history, atmospheric oxygen remains low. Life exists for an immense period before oxygen becomes easy to detect remotely. A distant observer examining the early Earth might conclude that the planet is lifeless. The observer would be wrong. The planet would contain oceans filled with microorganisms. Biology would be active, but its atmospheric signature would remain subtle. This creates an important challenge. A living planet may not resemble modern Earth. It may resemble ancient Earth. Its atmosphere may contain methane, carbon dioxide, nitrogen, and water vapor, while holding very little oxygen. Its life may remain microbial. Its biosphere may be large yet difficult to detect. The absence of oxygen is therefore not evidence of absence. It may simply describe a different stage in planetary history. Oxygen can also accumulate without life. A planet close to its star may experience a powerful greenhouse process. Water evaporates into the atmosphere. High above the surface, ultraviolet light breaks water molecules into hydrogen and oxygen. The lighter hydrogen escapes into space more easily. Oxygen remains behind. Over time, the planet may develop a large oxygen-rich atmosphere, even though its oceans have been lost. Such a world could appear promising at first glance. Further study might reveal that it is extremely hot and dry. The oxygen would record the destruction of water rather than the activity of biology. Small planets around red dwarf stars may face similar complications. Young red dwarfs can emit strong ultraviolet and X-ray radiation. A nearby planet's upper atmosphere may lose hydrogen rapidly. Abiotic oxygen may gather. The same star that makes a planet easy to observe can also create a misleading signal. Scientists therefore search for additional clues. If oxygen appears alongside abundant carbon monoxide, for example, non-biological photochemistry may be important. If water vapor is absent and the planet is extremely hot, an ocean loss scenario becomes more likely. If oxygen appears with methane in a temperate atmosphere and no obvious geological process can maintain both, biology becomes a stronger possibility. The atmosphere must be read as a whole. Ozone offers another potential sign. Ozone consists of 3 oxygen atoms. It forms when ultraviolet light interacts with ordinary molecular oxygen. On Earth, ozone gathers mostly in the stratosphere and absorbs harmful ultraviolet radiation. Because ozone can be easier to detect than oxygen under some conditions, it may serve as an indirect indicator of an oxygen-rich atmosphere. A planet with abundant ozone may possess a significant supply of molecular oxygen. Again, the origin would need careful examination. Ozone is not produced directly by life. It arises from atmospheric chemistry. Its value comes from its relationship with oxygen, which on Earth is strongly biological. Methane provides a different window. On early Earth, methane may have been more abundant than it is today. Microorganisms called methanogens produce methane in environments without oxygen. They live in wetlands, sediments, animal digestive systems, and deep underground. Their metabolism is ancient and simple. Some combine hydrogen with carbon dioxide. The reaction provides energy and releases methane. A planet dominated by microbial life might therefore develop a methane-rich atmosphere without much oxygen. Methane absorbs infrared light and can influence climate. On the young Earth, it may help keep the surface warm, while the sun is fainter than it is today. A distant world with methane, carbon dioxide, liquid water, and a suitable temperature could become an important target. The challenge is that methane has many non-biological sources. It can emerge from volcanoes. It can be released by impacts. It can form when water interacts with iron-rich rock in a process associated with serpentinization. A methane detection becomes more interesting when its abundance is difficult to explain geologically. Its relationship with other gases also matters. Large amounts of methane together with oxygen would be unusual because the two react. Methane combined with carbon dioxide and very little carbon monoxide may also carry information under certain planetary conditions. No simple rule applies to every world. Each atmosphere follows its own chemistry. Carbon dioxide is another central gas. It is not considered a biosignature by itself because volcanoes, rocks, oceans, and sunlight all influence its abundance. Yet carbon dioxide is essential to understanding habitability. It traps heat. It participates in weathering. It dissolves in water. It provides carbon for photosynthesis. The amount of carbon dioxide may reveal whether a planet can maintain surface temperatures suitable for liquid water. On Earth, a long-term carbon cycle helps stabilize climate. Volcanoes release carbon dioxide. Rainwater absorbs some of it and becomes mildly acidic. The water reacts with exposed rock. Rivers carry dissolved material into the ocean. Carbon becomes stored in sediments and minerals. Plate tectonics eventually carries some of this material into Earth's interior. Volcanism returns carbon dioxide to the atmosphere. The cycle operates slowly, across millions of years. It acts like a geological thermostat. When Earth warms, weathering tends to accelerate and remove more carbon dioxide. When Earth cools, weathering slows while volcanic release continues. The balance is not perfect, but it helps maintain long-term habitability. A distant rocky world with carbon dioxide, water, active geology, and moderate temperatures may possess a similar stabilizing system. Such a cycle would not prove life. It would indicate that the planet has remained hospitable long enough for life to have a chance. Water vapor is equally important. It confirms that water exists in the atmosphere. It may arise from oceans, lakes, ice, or humid air. Water leaves strong absorption features in infrared light. Astronomers have detected water vapor in the atmospheres of several exoplanets, especially large hot worlds. Detecting it around a small rocky planet is more difficult. The signal is faint. Clouds can hide lower atmospheric layers. Haze can flatten the spectrum. The star itself may contain spots and active regions that complicate the measurement. Even so, water remains one of the first molecules scientists seek. A planet with atmospheric water, moderate temperature, and a stable surface becomes more interesting than a dry world. Yet water alone does not imply habitability. Venus may once have had oceans, but its present atmosphere is extremely hot. Gas giants contain water in deep atmospheric layers, while lacking solid surfaces like Earth's. Some exoplanets may possess water vapor, because their atmospheres are heated far beyond conditions suitable for familiar biology. Every molecule must be placed within the larger planetary story. Nitrous oxide is another proposed biosignature. On Earth, microorganisms produce much of it through processes connected to the nitrogen cycle. It can remain in the atmosphere long enough to become detectable in principle. Strong ultraviolet light can break it apart, and its abundance depends on the planet's environment. Non-biological sources are possible, though biological production dominates on modern Earth. A planet with nitrous oxide alongside oxygen and water might deserve close attention. The signal would likely be difficult to measure, but future telescopes may improve the search. Other gases have also been suggested. Methyl chloride is produced by some organisms on Earth. Dimethyl sulfide is associated largely with marine life, especially microscopic organisms in the ocean. Ammonia might become a biosignature under certain atmospheric conditions if life produces it faster than sunlight and chemistry remove it. Some researchers examine gases that do not occur naturally in large amounts and might suggest technology rather than biology. These are sometimes called technosignature gases. Industrial pollutants could, in theory, alter a planet's spectrum. the idea remains highly speculative. A civilization would need to produce enormous quantities, and the gases would need to survive long enough to be observed. Still, the concept expands the search from natural biospheres to technological activity. Life might change a planet accidentally through metabolism. Intelligence might change it deliberately or industrially. Atmospheric chemistry provides clues to both possibilities. The study of exoplanet atmospheres begins with light. A star emits a broad range of wavelengths. When a planet passes in front of the star, most starlight continues toward Earth. A small portion travels through the planet's atmosphere. Molecules within the atmosphere absorb specific wavelengths. The missing light creates dark features in a spectrum. Each molecule has its own pattern. Water absorbs one collection of wavelengths. Methane absorbs another. Carbon dioxide, oxygen, ozone, and sodium each leave different signatures. The result resembles a barcode written by the atmosphere. The signal is extremely small. The planet may block only a tiny fraction of the star. The atmosphere blocks an even smaller fraction. Telescopes must measure minute changes while correcting for instrumental effects, stellar activity, and noise. Observations are often repeated across several transits. The data are combined. Models compare possible atmospheric compositions. Slowly, a probable picture emerges. The first exoplanet atmospheres studied in this way belong mostly to hot gas giants. Their large sizes and expanded atmospheres make them easier targets. Astronomers detect sodium, water vapor, carbon monoxide, and other compounds. They observe clouds, hazes, and differences between the hot and cool regions of tidally locked planets. These worlds are unlikely to support life as known on Earth. They serve as training grounds. Every measurement improves techniques that may later be used on smaller, cooler planets. The James Webb Space Telescope adds powerful infrared capabilities. It can study atmospheric molecules in greater detail than many earlier observatories. Webb examines worlds ranging from giant planets to smaller rocky bodies. Some results provide clear detections. Others reveal flat spectra that may indicate clouds, haze, thin atmospheres, or no atmosphere at all. A non-detection is also useful. It shows that certain worlds may have lost their air. It narrows the conditions under which planets around small stars can remain habitable. Rocky planets orbiting red dwarfs are among the most accessible targets. Their stars are small. When an Earth-sized planet crosses one, it blocks a relatively large fraction of the light. The habitable zone lies close to the star, so transits repeat frequently. Yet these systems remain challenging. Red dwarfs are active. Their surfaces contain dark spots and bright regions. Flares alter ultraviolet radiation. The star's own atmosphere can leave spectral patterns that resemble or obscure planetary signals. A planet may also be tidally locked and exposed to strong stellar winds. Astronomers must separate the planet from the star with great care. The TRAPPIST-1 system is a major example. Its 7 small planets provide several opportunities to study rocky atmospheres. The innermost worlds receive strong radiation and are likely too warm for surface liquid water. The outer worlds receive less energy. Several occupy regions where moderate temperatures are possible under suitable atmospheres. Observations attempt to determine whether these planets retain air. A thick atmosphere would redistribute heat between the day and night sides. It would also create detectable absorption features. A bare rocky surface would behave differently. The measurements are difficult, but each observation adds to a long-term portrait of the system. One important technique studies secondary eclipses. A secondary eclipse occurs when a planet passes behind its star. Before the eclipse, the telescope receives light from both the star and the planet. During the eclipse, the planet disappears from view. The tiny difference reveals the planet's contribution. For hot planets, this can provide information about thermal emission and temperature. If a rocky planet is extremely warm on its day side and very cold elsewhere, it may lack a substantial atmosphere. A thick atmosphere would carry heat around the globe and reduce the contrast. Temperature measurements therefore help determine whether a planet possesses air, even when individual gases are not detected. Another technique uses direct imaging. Instead of waiting for a transit, a telescope attempts to separate the faint light of a planet from the overwhelming glare of its star. This is extraordinarily difficult. A star can be billions of times brighter than an Earth-like planet seen in reflected light. The two objects may appear separated by only a tiny angle. Special instruments called coronagraphs block part of the starlight. Other designs use external star shades that fly far from a telescope and cast a precise shadow. Adaptive optics corrects for Earth's moving atmosphere when observations are made from the ground. Direct imaging has already captured several young giant planets located far from their stars. These planets glow strongly in infrared because they retain heat from formation. Imaging an Earth-like world is a greater challenge. Future observatories are being designed with this goal in mind. A direct spectrum of a small temperate planet could reveal oxygen, water, methane, clouds, and surface reflection. It could transform a faint point into a chemical world. Surface light itself may carry biosignatures. Plants on Earth absorb visible light for photosynthesis. They reflect strongly in the near-infrared. This sudden increase in reflectance is called the vegetation red edge. Seen in a spectrum, it creates a distinctive change across wavelengths. A distant planet covered in vegetation might display a similar feature. Alien photosynthetic organisms would not necessarily use chlorophyll. Their pigments might absorb different colors depending on the star's light and the planet's atmosphere. Around a red dwarf, useful light arrives in different proportions. Organisms might appear dark, purple, orange, or another color. The general idea is not to search only for green. It is to search for a surface pattern that ordinary minerals cannot easily explain. Earth contains organisms with many pigments. Purple bacteria use forms of photosynthesis, different from those of plants. Algae display red, brown, and golden colors. Microbes living beneath strong sunlight produce protective pigments. An inhabited exoplanet may have a spectral edge at an unfamiliar wavelength. Researchers model these possibilities, so future observations do not depend on a single Earth-centered expectation. Ocean glint may provide another surface clue. When light reflects from a smooth liquid surface at the correct angle, it produces a bright glimmer. Satellites observe this effect on Earth. A distant planet with large oceans may show changing brightness as it moves through its orbit. Clouds complicate the signal. Ice can also reflect strongly. Yet a repeating pattern consistent with specular reflection could suggest open liquid. Combined with water vapor and moderate temperatures, ocean glint would strengthen the picture of a habitable world. Seasonal changes may also reveal life. On Earth, vegetation grows and fades with seasons. Atmospheric carbon dioxide rises and falls as plants absorb it and organic matter decays. Oxygen changes slightly. Methane sources vary. The surface color of large regions shifts. A distant planet observed over many years might show repeating changes. Seasons can also arise from non-biological processes. Carbon dioxide can freeze and evaporate. Dust storms alter brightness. Clouds move. A seasonal biosignature would need to match biological cycles more closely than ordinary climate patterns. Time becomes part of the evidence. A living world may breathe slowly across its year. Clouds create both challenges and opportunities. They hide surface features and flatten atmospheric spectra. A thick cloud layer can make it difficult to measure gases below. Venus demonstrates how completely clouds can conceal a planet. From space, its surface remains invisible in ordinary light. Yet clouds also reveal atmospheric circulation and the presence of condensable substances. Water clouds may indicate a hydrological cycle. Their altitude, thickness, and distribution affect climate. On a tidally locked planet, bright clouds may gather above the region facing the star. They could reflect enough energy to prevent overheating. A world once assumed too close to its sun might remain temperate because of cloud cover. Weather is therefore part of habitability. It moves heat, it carries water, it shapes the chemical environment where life might exist. Haze provides another layer. Early Earth may have contained an organic haze produced by methane chemistry. Titan possesses a thick haze today. A haze can cool a planet by reflecting sunlight while warming parts of the atmosphere by absorbing radiation. Its spectral features may indicate rich carbon chemistry. On a planet with methane and carbon dioxide, an organic haze might suggest active production of methane. Biology could be one source. Non-biological processes could also contribute. The haze would not be proof. It would become one piece of a larger atmospheric puzzle. The central difficulty in biosignature science is the possibility of false positives. A false positive occurs when a non-living planet produces a signal that resembles life. Oxygen created through water loss is one example. Methane produced by geology is another. Surface minerals may mimic biological pigments. Atmospheric chemistry driven by unusual starlight may generate unexpected gases. The reverse problem also exists. A false negative occurs when life is present but not detected. A biosphere may be small. Its gases may dissolve in oceans or react with rocks. Clouds may hide the atmosphere. Life may exist underground or beneath ice, leaving almost no global signal. The planet may be in an early stage before oxygen accumulates. Earth itself would produce false negatives during much of its history. These challenges do not make the search impossible. They make it careful. Scientists build models of lifeless planets. They study how volcanoes, oceans, rocks, and ultraviolet light shape atmospheres. They recreate chemical reactions in laboratories. They observe Venus, Mars, Titan, and the giant planets to understand non-biological chemistry. They examine Earth across different geological eras. Every nearby world becomes part of the reference library. To recognize life elsewhere, science must first understand what lifeless chemistry can accomplish. Venus is especially important. It is nearly the same size as Earth. It may once have possessed water. Today it has a dense carbon dioxide atmosphere, sulfuric acid clouds, and extreme surface heat. Venus shows that an Earth-sized world in a neighboring orbit can follow a radically different path. Mars provides the opposite example. It loses much of its atmosphere and surface water. Titan demonstrates organic chemistry without known life. Jupiter and Saturn show complex atmospheric molecules in gas-rich environments. Together, these worlds prevent simplistic interpretation. The same molecule can mean different things in different places. Planetary context is everything. A strong biosignature case would likely combine several categories of evidence. The planet would occupy a region where liquid water is plausible. Its temperature would be moderate. Water vapor might appear in the atmosphere. Oxygen or ozone could be present. Methane might coexist at a level difficult to explain without continual production. Carbon dioxide would support climate without indicating an extreme greenhouse state. The star's radiation would be measured. The planet's mass and radius would suggest a rocky composition. Clouds and seasons might indicate an active hydrological cycle. Surface reflection could hint at oceans or pigments. No single clue would carry the conclusion. The pattern would. This resembles the way life is recognized in ancient Earth rocks. A strange shape alone is not enough. An unusual carbon ratio alone is not enough. A mineral alone is not enough. But when shape, chemistry, geological setting, and age all point toward biology, confidence grows. Distant planets will require the same patience. The first suspected biosignature may not be announced as final proof. It may begin as a spectrum containing an unexpected feature. Other telescopes will repeat the observation. Different teams will analyze the data. Models will test non-biological explanations. The star will be studied. The planet's orbit, mass, temperature, and atmospheric structure will be refined. Years may pass before the scientific community reaches agreement. The discovery of life may arrive gradually. It may not be a single moment. It may be a conclusion that becomes harder to avoid with every new measurement. There are also worlds that may possess biospheres without atmospheres easy to study. An ocean planet covered by deep water could hide much of its chemical activity. High-pressure ice may separate the ocean from the rocky interior, reducing nutrient exchange. An icy moon may support life below a frozen shell, while showing almost nothing at the surface. A dry planet may contain organisms underground. Atmospheric biosignatures favor life that interacts with a planet's air on a large scale. They may miss quiet biospheres. The search must therefore continue in several directions. Space missions examine nearby worlds directly. Telescopes study distant atmospheres. Radio observatories listen for artificial signals. Optical instruments search for unusual pulses. Astronomers examine planetary systems for structures or energy use that nature may not easily produce. Each method looks for a different kind of presence. Together, they cover more of the possibilities. The study of biosignatures also changes the way Earth is understood. The planet is not simply habitable because it lies at the correct distance from the Sun. It is habitable because air, water, rock, and life continuously interact. Microbes influence clouds. Plants alter atmospheric gases. Ocean organisms move carbon into sediments. Living roots break down stone. Animals transport nutrients. The biosphere participates in the planet's chemistry. Life is not merely resting on Earth, it is part of Earth. A distant observer would not see individual organisms. The observer would see their combined effect. Billions of cells and ecosystems leave a shared imprint in the atmosphere. This creates a gentle possibility. A faraway planet may already be carrying such an imprint. Its organisms may be too small to see. Its continents may be hidden behind cloud. Its oceans may reflect only a faint glimmer. Yet the atmosphere above it may contain gases that do not belong together. A telescope may collect a few photons that have passed through that air. Those photons may cross dozens of light years. They may enter a mirror near Earth. Inside their spectrum, a pattern may wait. Oxygen beside methane, water above a temperate surface, a seasonal change repeated year after year, a pigment shaped by a distant sun. None of these signs has yet provided universally accepted proof of extraterrestrial life. The search remains open, but the tools are now capable of asking the question directly. Not merely whether planets exist, not merely whether they are the right size, but what fills their skies. This is a profound change. For centuries, the atmospheres of other worlds remain beyond reach. Now light from those atmospheres can be separated and studied. Their gases can be named. Their temperatures can be estimated. Their clouds can sometimes be inferred. The first steps are delicate, and the conclusions remain cautious. Yet each spectrum brings a distant world slightly closer. A planet once known only by the pull it exerts on its star becomes a place with air. A transit becomes a climate. A faint shadow becomes a sky. Most atmospheres studied will not reveal life. Many planets will be too hot, too cold, too dry, or too unstable. Some will have lost their gases. Others will remain wrapped in thick hydrogen. But the galaxy contains an immense number of worlds. The search does not require every planet to be alive. It requires one clear example. One atmosphere whose chemistry cannot be explained by rock, water, sunlight, and chance alone. One world where the simplest explanation becomes biology. Until then, the work continues quietly. Telescopes gather light. Spectra grow clearer. Models become more precise. Nearby planets teach how lifeless atmospheres behave. Earth's history teaches how living atmospheres change. The universe does not need to send a message for life to be noticed. Sometimes, life simply changes the air around it, and across the darkness between stars, that altered air may become the first breath of another living world that humanity is able to recognize. Life does not need to become intelligent. For most of Earth's history, biology remains microscopic. Single cells fill oceans, sediments, rocks, and shallow pools. They gather energy, reproduce, and slowly transform the planet. Complex animals appear much later. Technology arrives only during the final, narrow moment of Earth's long history. This means that a living galaxy may still be a quiet galaxy. Millions of planets could contain microbes without producing a single radio transmitter. Oceans could hold complex ecosystems whose inhabitants never build machines. Intelligent species might arise and remain underwater, where fire and metallurgy are difficult. Others might develop tools without becoming interested in space. The search for extraterrestrial intelligence therefore asks a more specific question than the search for life. It does not ask only whether biology exists. It asks whether biology has learned to shape energy in ways that can be noticed across interstellar distance. A technological civilization may reveal itself differently from a forest or a microbial ocean. Living organisms change atmospheric chemistry. Technology may produce narrow radio signals, brief flashes of light, industrial gases, artificial illumination, large structures, or unusual patterns of heat. These possible signs are called technosignatures. A technosignature is evidence that may be best explained by technology. Like a biosignature, it must be interpreted carefully. Nature also creates radio bursts, bright pulses, strange chemical mixtures, and large amounts of infrared radiation. The universe is full of energetic processes. Stars flare, gas falls into black holes, magnetic fields accelerate particles, clouds of dust absorb light and release heat. A convincing technosignature must therefore show a degree of organization that ordinary physics does not easily produce by itself. The oldest and best-known search focuses on radio waves. Radio is a form of electromagnetic radiation, like visible light, infrared, ultraviolet, and X-rays. The differences between these forms arise from wavelength and frequency. Visible light occupies only a small part of the electromagnetic spectrum. Radio waves have longer wavelengths and generally lower frequencies. They can cross enormous distances through space. Many frequencies pass through Earth's atmosphere and reach telescopes on the ground. This makes radio a natural tool for both astronomy and communication. Humanity has been using radio technology for little more than a century. Television broadcasts, radar systems, satellite transmissions, and communication networks all release electromagnetic energy. Most of this radiation weakens rapidly as it spreads. A signal traveling outward does not remain concentrated. Its energy covers an ever-growing region, becoming fainter with distance. An ordinary broadcast may be difficult to detect from even a nearby star. Powerful radar transmissions are more promising because they can be intense and narrowly directed. A sufficiently sensitive extraterrestrial telescope, pointed toward Earth at the correct time, might notice some of them. Earth is therefore not surrounded by a bright radio shell containing every conversation and song ever transmitted. The signals spread, weaken, overlap, and become lost within natural and artificial noise. Yet the planet is not completely silent. Certain forms of technology could reveal that something unusual is happening here. The same principle guides the search elsewhere. Astronomers listen for signals that appear too narrow, too structured, or too precisely repeated to come easily from a natural object. Natural radio sources usually transmit across a range of frequencies. A star, galaxy, or cloud may create a broad spectrum. A technological transmitter can concentrate energy into a very narrow band. This is useful for communication because more power reaches the chosen frequency. It is also useful for detection. A narrow signal may stand out against a quieter background. The ideal extraterrestrial signal might resemble a thin line in a radio spectrum. It may drift slowly in frequency as the source planet rotates and orbits its star. That drift would be valuable. Earth's motion changes the apparent frequency of a signal through the Doppler effect. A planet turning beneath a transmitter creates a similar change. A steady signal arriving from a rotating, orbiting world may slide gently across frequency over time. Such motion could help distinguish a distant source from interference produced near the telescope. Human technology fills the radio spectrum. Satellites pass overhead. Aircraft communicate. Mobile networks transmit. Radar systems operate. Electrical equipment creates noise. A large part of modern radio astronomy involves separating the sky from Earth. A possible signal must appear in the direction of a star rather than across the entire horizon. It should behave consistently with celestial motion. It should repeat when the telescope returns to the same coordinates. Ideally, other observatories should detect it independently. This requirement makes the search patient. A signal that appears only once may remain interesting, but it is difficult to study. A signal that repeats can be measured, mapped, and tested. Perhaps the most famous single detection in the history of the search occurs in August 9. A radio telescope known as the Big Ear is observing the sky in Ohio. The instrument records a strong, narrow-band signal that lasts for 72 seconds. Astronomer Jerry Ehrman later notices the unusual sequence on a computer printout. He circles it and writes the word "wow" beside the data. The signal becomes known as the wow signal. Its properties attract attention. It is strong. It appears near a frequency associated with neutral hydrogen. It rises and falls in a manner consistent with a source passing through the telescope's observing beam. Yet it is never detected again. Repeated searches of the same region do not recover it. Without repetition, its origin remains uncertain. It may arise from a natural phenomenon not recognized at the time. It may involve terrestrial interference, though some simple explanations are difficult to reconcile with the observation. It may result from a temporary astronomical source. There is not enough information to reach a firm conclusion. The wow signal is not proof of another civilization. Its lasting importance lies in the way it illustrates the challenge. A moment of unexplained radio energy can invite many possibilities. Only repeatable evidence can turn possibility into knowledge. The universe contains many radio sources once mistaken for something artificial. In 1967, graduate student Jocelyn Bell Burnell notices regular pulses within data from a radio telescope. The pulses are remarkably precise. They repeat at short intervals. For a brief period, the source receives a playful label referring to little green men. The true explanation becomes even more extraordinary. The pulses come from a neutron star. A neutron star is the dense remnant left after certain massive stars end their lives. Its matter is compressed to extreme density. Some neutron stars rotate rapidly and possess strong magnetic fields. Beams of radio energy extend from their magnetic regions. As the star turns, the beams sweep through space. When one crosses Earth, a pulse is detected. The object is called a pulsar. Pulsars can keep time with remarkable stability. Their signals are organized, but entirely natural. This discovery teaches an important lesson. Regularity alone does not prove intelligence. Nature can build clocks. Nature can create beams. Nature can repeat a signal for millions of years. A technological explanation becomes convincing only after natural alternatives have been studied and rejected. Later, astronomers discover fast radio bursts. These are brief flashes of radio energy arriving from distant galaxies. Some occur once, others repeat. A few display complex patterns of activity. Their extraordinary brightness initially creates many questions. Today, at least some fast radio bursts are linked to highly magnetized neutron stars called magnetars. Their intense magnetic environments can release enormous bursts of energy. The details remain an active area of research, but the events are treated as astrophysical rather than artificial. Again, the universe demonstrates its ability to surprise. A strange signal does not weaken the scientific search, it improves it. Each natural discovery teaches astronomers how to recognize the background against which technology must be found. Radio searches examine millions of frequency channels at once. Modern instruments collect huge volumes of data. Computers identify narrow peaks, drifting signals, pulses, and repeating patterns. Most candidates are removed quickly because they correspond to known interference. A satellite may appear in several telescope directions. A local transmitter may return whenever the instrument points near the horizon. A signal may vanish when equipment is turned off. The small number of surviving candidates receive closer study. Projects connected with the search for extraterrestrial intelligence, commonly called SETI, have used many observatories. Some surveys target nearby stars. Others scan broad regions of the Milky Way. Some concentrate on planetary systems known to contain rocky worlds. Others look toward the galactic center, where stars are densely gathered. The question is not only where to listen, it is also when to listen, and at which frequency. The radio spectrum is vast. An extraterrestrial transmitter might use frequencies familiar to human engineers. It might use frequencies chosen for low background noise. It might communicate through methods not yet developed on Earth. A search can examine only part of this immense space at any one time. This creates what researchers sometimes call the cosmic haystack. The complete search includes direction, frequency, time, signal strength, bandwidth, repetition rate, polarization, and modulation. Even a large survey explores only a tiny part of all possible combinations. The absence of a detection does not mean the entire galaxy has been thoroughly examined. It means that specific regions of this vast search space have been checked. Humanity has dipped a small cup into a cosmic ocean. The cup may be empty, while the ocean remains unexplored. One proposed region for listening is known as the water hole. Neutral hydrogen naturally emits radio energy near a frequency of about 1.42 gigahertz. A molecule called hydroxyl has spectral lines at somewhat higher radio frequencies. Hydrogen and hydroxyl are the components of water. The relatively quiet region between some of these natural frequencies becomes a symbolic meeting place in the spectrum. A civilization familiar with astronomy might choose it deliberately. The idea is elegant, though entirely human. Another species may see no special meaning in the same region. It may choose frequencies based on its atmosphere, technology, star, or local sources of interference. There may be no universal radio channel. A deliberate beacon would be easier to detect than accidental leakage. A beacon is designed to attract attention. It may use a powerful transmitter and point toward promising stars. It may repeat a simple pattern. It could contain mathematical sequences, timing information, or changes that reveal intentional structure. Prime numbers are often suggested because they are not easily created by simple periodic processes. A sequence of pulses representing 2, 3, 5, 7, and 11 might imply a sender familiar with mathematics. Yet even a mathematically organized signal would require confirmation. The receiving instrument could introduce patterns. Human interference could imitate structure. Independent observatories would need to recover the same transmission. If a genuine beacon were confirmed, Understanding its content would be another challenge. Mathematics and physics may provide shared reference points. Hydrogen has the same spectral properties everywhere. The speed of light does not depend on culture. Atomic transitions could define units of time and length. Geometric relationships might be expressed through repeated patterns. More complex ideas would be harder. Language depends on shared experience. Words for ocean, sky, body, memory, and life arise from particular histories. A civilization beneath the ice of an ocean moon may organize reality differently from a species living on land. Meaning might need to be built gradually from simple relationships. Communication across interstellar distance is also slow. The nearest star system lies more than 4 light-years away. A message sent there requires over 4 years to arrive. A reply would take over 4 more. A simple exchange would unfold across nearly a decade. Communication with a civilization 100 light-years away would move across generations. A question asked today might receive a response 2 centuries later. This would not resemble an ordinary conversation. It would resemble archaeology carried out through light. Each message would preserve the knowledge and intentions of a civilization at an earlier time. The sender might change before the receiver answers. Governments could disappear. Languages could evolve. Technologies could be replaced. The stars would connect societies separated not only by distance, but by history. This delay makes a continuously broadcasting beacon especially useful. A beacon does not need to wait for a reply. It simply announces that someone exists. It may repeat the same information for centuries. Any civilization discovering radio astronomy could eventually notice it. Maintaining such a transmitter would require long-term commitment. The beacon might be automated. It could continue after its builders are gone. Humanity might one day receive a message from a civilization that no longer exists. The signal would still be evidence. It would show that intelligence arose somewhere else, even if the source world had changed. The search is not limited to radio. Visible and infrared light can also carry information. Lasers concentrate energy into narrow beams. A powerful laser pointed toward Earth could briefly outshine its host star at a particular wavelength. The flash might last only a fraction of a second. To detect it, instruments must observe the correct star at precisely the correct moment. Repeated pulses would be easier to recognize. This field is sometimes called optical SETI. A civilization might use lasers for communication between planets, spacecraft, or stars. Some beams could cross Earth's line of sight accidentally. Others might be deliberate. Lasers offer several advantages. They can transmit large amounts of information. Their narrow beams reduce wasted energy. They can operate at wavelengths where background starlight is manageable. Their precision is also a disadvantage for observers. A narrow beam covers only a small part of the sky. Unless it is aimed toward the solar system, Earth may never encounter it. Radio beams can also be narrow, but some transmission systems spread energy more broadly. The form of communication a civilization chooses will shape whether it can be detected. Technology may be widespread, while signals rarely point toward Earth. Astronomers also search for extremely short optical pulses. Natural objects do not usually produce perfectly synchronized bursts, lasting only billionths of a second. A repeated series of such flashes could be difficult to explain without technology. Special detectors monitor nearby stars for these events. The challenge remains one of time. A telescope may watch a star for minutes while a civilization transmits once each year. Or the transmitter may operate continuously in a direction that never crosses Earth. A quiet observation does not settle the question. Even without deliberate communication, large technological activity may alter a planet. Industrial processes can create gases rarely produced by nature. Some chemicals designed for refrigeration or manufacturing can remain in an atmosphere and absorb infrared light. On Earth, chlorofluorocarbons are human-made compounds, once used widely in industrial products. They affect atmospheric ozone and possess distinct spectral features. An advanced telescope observing Earth from far away might eventually detect extremely large concentrations of such gases. A distant civilization could manufacture entirely different compounds. Researchers therefore study broader categories of artificial atmospheric chemistry. The strongest candidates would be molecules with few plausible natural sources and long atmospheric lifetimes. Detecting them would be difficult. The concentration may be low. Other gases may hide the spectral features. Clouds could block the relevant atmospheric layers. A civilization may use clean technology that leaves little pollution. Industrial gases are therefore only one possible technosignature. They reflect a particular stage of development, not intelligence itself. Artificial illumination creates another idea. Cities brighten Earth's night side. From nearby space, the patterns are obvious. Across interstellar distance, they are extremely faint. A future telescope with immense sensitivity might attempt to detect unusual visible light from the dark hemisphere of an exoplanet. Natural processes also create night-side light. Auroras glow, lightning flashes, volcanoes release heat. Atmospheric chemistry produces faint air glow. A technological signature would need to show a spectrum, distribution, or regular pattern, unlike these natural sources. Perhaps the light would cluster near coastlines. Perhaps it would use narrow wavelengths associated with artificial lamps. Perhaps its intensity would remain stable despite weather. This remains beyond present capabilities for Earth-like planets, but it provides a direction for future instruments. Waste heat may offer a broader sign. Every technology uses energy. No process is perfectly efficient. Some energy eventually becomes heat and radiates away. A civilization using a significant portion of its planet's available energy could alter the infrared glow of the world. A much larger civilization using substantial energy from its star might produce an even stronger signal. This idea leads to one of the most famous proposed megastructures. In the 20th century, physicist Freeman Dyson considers how a growing civilization might obtain more energy. A planet receives only a tiny fraction of its star's total output. A sufficiently advanced society might build large numbers of orbiting collectors around the star. These objects could capture energy that would otherwise escape into space. The complete system is often called a Dyson sphere. The name may suggest a rigid shell surrounding a star. Such a shell would face serious engineering and stability challenges. A more plausible version is a Dyson swarm. It consists of many independent collectors traveling in orbit. Each structure captures starlight. Together, they may intercept a significant fraction of the star's energy. The energy would not vanish. After being used, much of it would become heat. The system might therefore appear dimmer in visible light and unusually bright in infrared. Astronomers have searched for stars with this combination. Dust can create similar infrared excess. Young stars are surrounded by dusty disks. Old stars release material. Collisions between asteroids generate fine particles. Dust absorbs visible or ultraviolet light and re-emits it as infrared radiation. Any candidate must be distinguished from these natural systems. No confirmed Dyson swarm has been found, yet the search demonstrates how ordinary astronomical data can be examined for signs of engineering. A civilization does not need to send a message. Its use of energy may reveal its presence. The scale of hypothetical civilizations is sometimes described through the Kardashev scale. A Type 1 civilization uses energy on a scale comparable to that available on its planet. A Type 2 civilization accesses energy comparable to the output of its star. A Type 3 civilization operates across much of a galaxy. These categories are broad thought experiments rather than precise predictions. Humanity has not reached Type 1 under the original conception. The scale helps researchers imagine what increasingly large engineering might look like. Planetary activity may alter atmospheric chemistry and surface temperatures. Stellar scale activity may change the spectrum of a star. Galactic activity could affect the infrared output of many stellar systems. No evidence confirms that civilizations reach these levels. Growth may not continue indefinitely. A stable society could choose efficiency rather than expansion. Advanced technology might become less visible instead of more visible. A civilization could move computation into cold regions where energy is used more efficiently. It could rely on compact systems. It might intentionally avoid announcing itself. Technological development does not need to follow a single path. Searchers therefore benefit from examining many kinds of signals. Some focus on communication. Some focus on energy. Some focus on atmosphere. Others examine movement. A spacecraft traveling through interstellar space might produce detectable effects. Powerful propulsion could release narrow beams or unusual radiation. A probe entering a planetary system might reflect sunlight or transmit data. Artificial objects could even exist within the solar system, though there is no confirmed evidence that any have been found. The solar system contains an enormous volume. Small objects are difficult to detect. Asteroids, comets, and debris move along many paths. Searching for an artificial probe would require identifying motion, shape, material, or signals inconsistent with natural bodies. This idea is sometimes connected to self-replicating probes. A civilization may find it more practical to send machines than biological travelers. A probe can survive long journeys without food or air. It can wait for centuries. It can study a star system and send information home. If it can use local material to build copies, it may gradually spread through the galaxy. Even at speeds far below light, a network of probes could cross the Milky Way on timescales shorter than the age of the galaxy. This leads to an important puzzle. If technological civilizations are common, and if some can spread machines between stars, why is there no clear sign of them? This question belongs to a larger discussion, often called the Fermi paradox. The paradox is not a formal contradiction. It is the tension between the immense scale and age of the galaxy and the lack of confirmed extraterrestrial evidence. The Milky Way contains hundreds of billions of stars. Many are billions of years older than the Sun. Planets appear common. Some civilizations, if they exist, could have begun long before humanity. Even slow expansion might cover the galaxy across millions of years, a short interval compared with cosmic history. Yet Earth has no confirmed visitors, artifacts, messages, or unmistakable engineering. The sky appears quiet. There are many possible explanations. Perhaps life itself is extremely rare. The transition from non-living chemistry to the first cell may require an unlikely combination of events. Earth may be one of very few places where it happens. Perhaps simple life is common, but complex life is rare. Earth remains dominated by microbes for billions of years. The development of large cells, multicellular organisms, nervous systems, intelligence, and technology may involve several difficult steps. Perhaps technological civilizations appear frequently, but do not last long. They may change direction, lose the ability to communicate, or become silent. They may use communication methods that human instruments cannot detect. Perhaps interstellar travel is more difficult than simple calculations suggest. Energy, radiation, maintenance, navigation, and long timescales may discourage expansion. Perhaps civilizations send probes, but the galaxy is so large that the solar system has not been visited. Perhaps evidence exists but is too faint, too brief, or too unfamiliar to recognize. The quiet sky does not point to one answer. It defines the mystery. One proposed explanation is called the Great Filter. The idea suggests that somewhere between lifeless matter and a galaxy-spanning civilization lies a step that is extraordinarily difficult. The filter might exist in the past. Perhaps the origin of life is rare. Perhaps complex cells are rare. Perhaps intelligence almost never develops. If humanity has already passed the hardest step, then complex technological life may be uncommon. The filter might instead lie in the future. Perhaps technological societies face challenges that prevent long survival or large-scale expansion. The concept is speculative and cannot yet identify any specific barrier. It organizes the uncertainty. Earth provides only one history. Without a second example of life, it is impossible to know which steps are easy and which are rare. Discovering microbes on Mars that began independently would suggest that life's origin is not the main filter. Finding complex ecosystems on many worlds would move the question farther forward. Detecting an ancient technological signal would show that intelligence has arisen elsewhere. Each discovery would reshape the puzzle. Another explanation is simple distance. The galaxy may contain many civilizations, but they may be separated by thousands of light years. Their radio leakage may be too weak to detect. Their active periods may not overlap. One civilization may broadcast for 500 years and then shift to another technology. Another may arise in the same region a million years later. Both exist within the history of the galaxy, but never at the same time. The Milky Way is not only large in space, it is large in time. Civilizations may pass through it like brief lights in a long night. Humanity's technological period is extremely short. Radio astronomy has existed for little more than a century. Systematic searches have examined only a small fraction of the sky, frequencies, and possible signal types. Expecting an immediate detection may be like entering a forest for 1 minute, hearing no birds, and concluding that none exist. The forest could be quiet at that moment. The birds may use frequencies outside human hearing. They may be far beyond the nearest trees, or there may truly be no birds. A longer observation is needed. Civilizations may also become less detectable as their technology improves. Early radio systems leak energy broadly. Modern communication increasingly uses cables, fiber optics, directional beams, and efficient transmission. Earth may become quieter at some radio frequencies, even while its technology becomes more advanced. A distant civilization could follow a similar path. Its easily detectable phase might last only a few centuries. Unless another observer listens during that interval, the planet appears silent. Deliberate beacons would avoid this problem, but there is no reason to assume every civilization builds them. A beacon consumes resources. Its purpose must be maintained across generations. The society must decide that being discovered is valuable. Alien cultures may not share that goal. Some researchers have considered whether advanced societies might intentionally avoid contact. This family of ideas is sometimes associated with the zoo hypothesis. A civilization could observe developing worlds without revealing itself. There is no evidence that this is occurring. The proposal demonstrates how difficult it is to draw conclusions from silence. Almost any behavior can be imagined. Scientific progress requires testable predictions. A hypothesis that explains every possible result, including permanent silence, is difficult to evaluate. For this reason, active searches focus on measurable signals rather than stories about unknown intentions. Another possibility is that intelligence rarely produces technology recognizable from a distance. Dolphins display complex communication and social behavior, yet they do not build radio telescopes. Octopuses solve problems and manipulate objects, but their lives are short and largely solitary. Human technology depends on a long combination of traits and circumstances. Hands allow precise manipulation. Language transfers knowledge. Long childhoods support learning. Social groups preserve skills. Fire permits cooking and metallurgy. Land environments make combustion easy. No single feature guarantees technology. An intelligent ocean species beneath the ice of Europa might understand its surroundings deeply while never discovering stars. Its civilization, if that word applies, could remain hidden beneath kilometers of water and ice. It may develop sound-based communication, biology, and mathematics without producing radio waves that escape into space. The galaxy could contain intelligence that astronomy cannot hear. Technology may also arise in forms that do not resemble machinery. The civilization might engineer living systems instead of metal devices. It could grow structures, store information in biological molecules, or alter ecosystems with extreme precision. Its planet might look natural from far away. Human searches are shaped by human history. Radio, lasers, industrial gases, and solar collectors are visible possibilities because they are understandable from present technology. Another civilization may discover entirely different methods. Even so, physics creates some shared boundaries. Information must be carried by something. Energy must be used. Heat must eventually be released. Matter must move. These universal requirements make the search possible, even when the specific engineering is unfamiliar. Artificial patterns may also appear in the timing of astronomical events. A civilization could modify the light from its star to create a recognizable sequence. Large orbiting structures might produce unusual transits. Ordinary planets create smooth, repeating dips in starlight. An artificial object with an unusual shape or collection of objects could create a more complex pattern. Astronomers examine strange light curves for this reason. The best-known example is a star called KIC 84628552, sometimes known as Boyajian's star or Tabby's star. The star displays irregular and unusually deep dimming events. Some early discussion considers whether large artificial structures could be responsible. Further observations support explanations involving dust. Different wavelengths are blocked by different amounts, as expected when small particles pass in front of the star. No radio or optical technosignature is confirmed from the system. The episode provides a useful example of scientific caution. An unusual observation encourages imaginative hypotheses. Additional data then tests them. A natural explanation does not make the original mystery unimportant. It improves the understanding of stellar and circumstellar environments. Similar searches continue across large collections of stellar brightness data. Modern sky surveys monitor millions or billions of objects. Computers can identify unusual dimming, unexpected motion, or rare spectra. Most anomalies will be natural. A small number may reveal new astrophysics, and among them, in principle, could be evidence of technology. The search for technosignatures is therefore closely connected with ordinary astronomy. The same telescope that studies galaxies can look for excess infrared heat. The same instrument that finds exoplanets can notice unusual transits. The same radio array that maps hydrogen can search for narrowband transmissions. No separate universe is required. Technology, if it exists, must leave traces within the physical universe already being observed. Humanity has also sent a few deliberate messages. In 1974, the Arecibo radio telescope transmits a brief, powerful signal toward the globular cluster Messier 13. The message encodes information using a sequence of binary digits. Its arrangement represents numbers, chemical elements, a simplified DNA structure, a human figure, the solar system, and the telescope. The target lies about 25,000 light-years away. The cluster will move during the signal's journey, and any reply would take tens of thousands of years. The transmission is therefore more a demonstration than a practical attempt at conversation. Spacecraft carry more physical messages. Pioneer 10 and Pioneer 11 include plaques showing human figures and astronomical information. Voyager 1 and Voyager 2 carry golden records. The records contain sounds, music, greetings, images, and scientific diagrams. The spacecraft travel outward from the solar system, but they move slowly compared with the distance between stars. They are unlikely to pass near another planetary system for an immense period. Their messages are bottles released into a cosmic sea. Their greatest value may be symbolic. They express the hope that knowledge can cross distance. They also capture a portrait of Earth at one moment in time. If discovered far in the future, the records would represent a civilization from the ancient past. Humanity must also consider whether deliberate transmission is wise. This activity is sometimes called messaging extraterrestrial intelligence, or METI. Supporters argue that Earth already produces detectable signs and that communication could bring knowledge of profound value. They note that interstellar distances make rapid physical consequences unlikely. Critics argue that humanity knows too little about possible recipients. They believe that decisions affecting the entire planet should not be made by small groups without broad discussion. There is no global agreement. The debate involves science, ethics, politics, philosophy, and risk. Listening is generally less controversial because it does not intentionally increase Earth's visibility. Transmitting announces a presence. The question is not only whether a message can be sent, it is who has the authority to speak for Earth. A genuine detection would create similar challenges. Scientists would need to confirm the signal. Observatories around the world would attempt independent measurements. Data would need to be protected from misunderstanding and false claims. Governments, scientific organizations, media, and the public would respond. No single country owns the sky. No single institution represents humanity. A signal containing information might require decades of study. Deciding whether to reply could become one of the largest collective decisions ever faced. Yet before these questions become immediate, the evidence must be real. The history of SETI contains many false alarms. Some originate from satellites. Some come from observatory equipment. Microwave ovens once create puzzling radio bursts at an Australian telescope when their doors are opened before the heating cycle finishes. These signals are given the name peritons. For years, their source remains uncertain. Eventually, careful testing connects them to local equipment. The discovery is almost humorous, but it carries a serious lesson. A signal can appear astronomical until every ordinary explanation is checked. In another case, a promising narrowband signal is detected in the direction of Proxima Centauri, the nearest star to the Sun. The candidate receives close attention because it appears during observations of a nearby planetary system. Later analysis indicates that it is most consistent with human-made radio interference. The original detection still improves search methods. Researchers learn how complex interference can imitate a drifting celestial signal. False alarms are not failures. They are rehearsals. Each one strengthens the procedures needed for a genuine discovery. The ideal detection would survive every test. It would be observed by multiple instruments. It would appear from a fixed direction in the sky. Its frequency drift would match motion in another planetary system. It would repeat. It might contain organized modulation or information. Natural astrophysical explanations would fail to reproduce its properties. Terrestrial and satellite interference would be excluded. Confidence would rise step by step. Even then, scientists may use careful language. They might first describe an unexplained narrowband source, then a candidate technosignature. Only after extensive confirmation would the word intelligence become appropriate. The evidence must carry the conclusion. This patience may make the discovery feel gradual. The public often imagines a sudden message arriving in clear language. Reality may begin with a thin line on a graph, a small excess of infrared light, a sequence of pulses, an atmosphere containing an unusual industrial compound. Years of observation may be required to understand what it means. Yet the quietness of the process does not reduce its importance. A single confirmed technosignature would show that intelligence is not unique to Earth. It would mean that evolution has produced another species capable of understanding and manipulating nature. Even without direct communication, humanity would know that thought has appeared elsewhere. Somewhere beneath another sky, matter has become curious. It has measured its world. It has discovered patterns. It has learned to store knowledge outside the body. It has shaped energy and sent an effect into space. The signal might come from nearby. It might cross half the galaxy. Its builders could be younger than humanity, or millions of years older. They might still exist. They might be gone. The signal would remain a bridge between two independent histories of life. Until such evidence appears, the search continues with no guarantee of success. Radio telescopes listen across wide bands. Optical instruments watch for brief pulses. Infrared surveys examine the heat of stars and galaxies. Exoplanet telescopes study atmospheric chemistry. Computers search enormous archives for patterns no one noticed before. Every year, the search becomes broader. More planets are known. More nearby stars are characterized. Instruments become more sensitive. Interference rejection improves. Artificial intelligence helps identify rare signals within large datasets. Humanity is learning not only how to listen, but how to recognize what it hears. The silence so far is real, but it is not complete. Most stars have never been observed with sufficient sensitivity across every useful frequency. Most have been studied only briefly. Many parts of the galaxy remain difficult to examine. Technological activity may be intermittent. Signals may be narrow. Civilizations may be distant. The search has only begun. For thousands of years, the stars are visible but unreachable. During the last few centuries, humanity learns that they are suns. During the last few decades, planets are found around them in great numbers. Now their atmospheres are beginning to be measured. The next step is to ask whether any of those worlds are not merely present, but aware. No answer has yet crossed the instruments with certainty. No confirmed beacon repeats from the dark. No unmistakable engineering surrounds a distant star. The absence of proof must remain part of the story. Yet the possibility is no longer separated from science. It can be tested. It can be measured. It can be searched for with real telescopes using known physical laws. Perhaps the first sign will be a narrow radio tone drifting gently as another planet turns. Perhaps it will be a laser pulse repeated at mathematical intervals. Perhaps it will be a strange atmosphere shaped by industry. Perhaps it will be heat surrounding a star whose light has been carefully gathered. Or perhaps the galaxy will remain quiet through many generations of listening. Either result will teach something profound. For now, Earth continues to send its own faint traces outward. Radar beams leave the planet. Spacecraft move beyond the planets. Artificial light glows across the night side. Atmospheric chemistry records the activity of billions of living beings and their machines. From sufficiently far away, humanity is also only a possible signal. A distant observer might be listening at the wrong frequency. Its telescope might not yet be sensitive enough. It might see the sun and know that planets are present, while remaining uncertain whether one is alive. Across the space between stars, two civilizations could search for each other and still miss. Their beams may pass at different times. Their instruments may study different wavelengths. Their brief technological ages may fail to overlap. But the act of listening carries its own quiet meaning. A species formed from ancient stars has learned to examine the darkness around those stars. It has built instruments larger than buildings. It has collected whispers of radio energy from across the galaxy. It has separated planetary atmospheres from distant starlight. It has begun to ask whether another mind is asking the same question. The universe has not yet answered clearly. Still, night after night, the telescopes remain open, and somewhere within the wide ocean of frequencies, there may be a signal already traveling toward a world prepared to hear it. The search for life beyond Earth contains many moments of almost discovery. A spacecraft measures an unexpected reaction. A telescope notices a molecule in a distant atmosphere. A meteorite contains shapes that resemble tiny fossils. A pilot observes something that cannot immediately be identified. For a brief moment, each mystery seems capable of changing humanity's understanding of the universe. Then the slower work begins. The instruments are examined, the observations are repeated, alternative explanations are tested, new measurements are collected. What first appears extraordinary often becomes chemistry, geology, atmospheric motion, interference, or a limitation in the original data. This does not make the search less meaningful. It reveals how carefully the universe must be studied. An unexplained observation is not the same as proof. The word unexplained means only that the available information is incomplete. It does not automatically point toward life, intelligence, or technology. The distance between a mystery and a discovery is filled with patient verification. That distance may be where some of the most valuable science occurs. Every uncertain result teaches researchers how planets behave. Every disputed signal improves future instruments. Every possible biosignature reveals another way that non-living chemistry can resemble biology. The almost discoveries prepare science for the day when the evidence may finally remain. One of the earliest and most fascinating examples begins on Mars. In 1976, NASA's Viking 1 and Viking 2 landers reach the Martian surface. They become the first successful missions designed to perform biological experiments directly on another planet. Each lander carries a small laboratory. The instruments are built to test whether microorganisms might live within the Martian soil. The experiments cannot search for every possible form of biology. They are designed around certain properties of Earth's microbes. Living cells often absorb nutrients. They exchange gases. They transform carbon-bearing molecules. They respond differently from sterilized material. The Viking landers therefore collect soil and expose it to carefully prepared conditions. One instrument is called the labeled release experiment. It places a nutrient solution containing radioactively marked carbon onto a Martian soil sample. If microorganisms consume the nutrients, they may release radioactive gas that the instrument can measure. The experiment produces a response. Gas appears soon after the nutrients touch the soil. The result is repeated at both Viking landing sites. A control sample heated to a high temperature behaves differently, as might be expected if heat had destroyed living organisms. For a moment, the experiment seems to have detected metabolism on Mars. NASA's Viking biology instruments did observe unexpected chemical activity, but the combined experiments did not provide definitive evidence of microorganisms at either landing site. Other Viking results make the interpretation more difficult. A separate instrument searches for organic molecules in the soil. Organic molecules are not proof of life, but they are expected in environments containing familiar organisms. The instrument does not detect them at the sensitivity available at the time. The Martian surface also appears highly reactive. When soil is moistened, chemical compounds within it can release oxygen and produce reactions that resemble metabolism. Sunlight and radiation may create powerful oxidizing substances in the soil. These substances can react with the nutrient solution without the presence of a cell. The positive signal may therefore come from unusual Martian chemistry. The experiments were prepared for an unfamiliar planet, but the planet proved even less familiar than expected. Mars did not provide a simple living or non-living answer. It produced a chemical puzzle. Most scientists concluded that Viking had not demonstrated life. Gilbert Levin, who led the labeled release experiment, continued to argue that its results were consistent with microbial activity. The debate remained because the experiment produced a response with several lifelike features. Yet a result can resemble biology without proving biology. The entire context must agree. Independent measurements should support the same conclusion. Organic material should be identified. The reaction should be difficult to reproduce through geology or chemistry alone. Viking could not satisfy every requirement. Its result remains one of the most intriguing ambiguous measurements in planetary exploration. The landers may not have discovered organisms, they did discover that detecting organisms is far more difficult than simply adding food to soil. The lesson influences later missions. Modern spacecraft do not rely on one biological reaction. They study the geological setting. They examine mineral history. They search for organic molecules preserved inside protected rocks. They measure isotope patterns. They investigate whether water once remained stable. They try to understand the environment before interpreting possible signs of life. The question has changed from a single experiment to a network of evidence. Viking also raises another possibility. The experiment itself may have changed the material it was trying to study. The Martian surface is extremely dry. If hypothetical organisms are adapted to tiny amounts of moisture, adding liquid water might place them under chemical stress. The nutrient mixture may also have been unfamiliar. Earth microbes living in deserts do not necessarily respond well to sudden flooding. This idea remains speculative. It cannot recover information that Viking did not collect. It simply shows how difficult it is to design an experiment for life with unknown chemistry. An instrument carries assumptions. It expects organisms to use certain nutrients. It expects them to react within a certain period. It expects a biological process to produce a measurable signal. Alien biology may not follow those expectations. Even Earth contains organisms that would be missed by many simple tests. Some grow slowly, some remain dormant, some use chemicals unfamiliar to most surface ecosystems. Some depend on relationships with other organisms and cannot survive alone in a laboratory container. The first Martian life experiment, therefore, becomes a quiet lesson in humility. A planet cannot always be understood through a single earthly recipe. Another almost discovery begins with a stone found in Antarctica. The meteorite is called Allen Hills 8401, or ALH 8401. It is an ancient piece of Mars. A large impact once throws the rock away from the Martian surface. It travels through space for a long period and eventually falls onto the Antarctic ice. Researchers recover it in Its Martian origin is revealed through its chemistry and trapped gases. The rock is extremely old. It formed during the early history of Mars, when the planet may have possessed thicker air and more liquid water. Inside the meteorite are small carbonate structures. There are organic compounds. There are crystals of magnetite. There are tiny shapes that under powerful microscopes appear somewhat like fossilized microorganisms. In 1996, a research team proposes that several features together may record ancient Martian life. The announcement captures worldwide attention. For the first time, scientists appear to possess possible physical remains of organisms from another planet. The evidence is not based on one observation. It is based on a collection of clues. The carbonates form in the presence of liquid water. Organic material rests near them. Some mineral structures resemble those associated with microbes on Earth. The smallest forms appear like tiny cells. Each detail seems to support the others. Yet each detail also has a possible non-biological explanation. The apparent fossils are extraordinarily small. Some are smaller than most known free-living cells. The shapes may be mineral structures rather than organisms. Organic compounds can form without biology. Meteorites carry them naturally. Contamination can also enter a rock after it reaches Earth. Magnetite crystals may be produced by geological processes involving heat, water, and rock. Carbonate minerals do not require life. The evidence slowly becomes less unified. Instead of several clues pointing toward one biological explanation, researchers find several geological processes capable of producing them separately. Later work examines the organic carbon within ALH 8401 in greater detail. A NASA-supported study reported in 2022 concluded that the material formed through non-biological reactions between water and Martian rock, including processes related to serpentinization and carbonation. The meteorite does not become unimportant. Its story changes. Instead of preserving confirmed fossils, it preserves ancient Martian chemistry. Water once moves through the rock. Minerals react. Organic compounds form without organisms. This is valuable because prebiotic chemistry must exist before biology can begin. The rock demonstrates that Mars can naturally produce some of the carbon-rich material from which life might eventually emerge. It also reveals a background signal. When future missions search for Martian fossils, they must distinguish biological organic matter from organic matter created by geology. The difference may be subtle. Both may contain carbon. Both may appear beside minerals formed in water. Both may create microscopic structures. Life does not use a separate set of atoms. It uses the same chemistry that exists before life. The boundary between geochemistry and biochemistry can therefore be difficult to recognize after billions of years. ALH 84001 becomes a practice case. Scientists learn which mineral shapes are unreliable. They learn how contamination can enter meteorites. They develop better instruments for studying isotopes and molecular structures. The apparent discovery fades, but the search becomes more capable. The meteorite also changes public expectations. Proof of extraterrestrial life may not arrive as a complete organism. It may arrive as a pattern within stone, a pattern of carbon isotopes, a repeating cellular texture, a collection of minerals difficult to produce together without metabolism. Such evidence will need to survive years of testing. A fossil from another planet cannot be accepted simply because it looks familiar. Rocks create spheres, tubes, filaments, and layered structures. Crystals grow into shapes that resemble biological organization. A convincing fossil must belong to a suitable geological environment. Its chemistry must support biological activity. Its size and structure must be compatible with cells. Several independent methods must point toward the same origin. The more extraordinary the conclusion, the more complete the pattern must become. Another almost discovery appears much closer to Earth. Venus is similar to Earth in size and mass. It may once have contained liquid water. Today it is hidden beneath thick clouds. Its surface is hot enough to melt some metals. Its atmosphere is dominated by carbon dioxide. Clouds contain droplets of sulfuric acid. The ground is not considered a likely home for familiar life. Higher within the atmosphere, however, temperatures and pressures become milder. Some researchers have wondered whether microorganisms could survive inside cloud droplets. The idea is difficult. The droplets are extremely acidic and contain very little available water. Yet Earth contains airborne microbes, and some organisms tolerate strong acidity. Venusian cloud life remains a possibility to test, not an established habitat. In 2020, astronomers report the apparent detection of phosphine in Venus's atmosphere. Phosphine is a molecule containing phosphorus and hydrogen. On Earth, it is associated with certain biological environments and industrial activity. It can also form naturally under high pressures and temperatures, such as those found deep within giant planets. Producing significant phosphine in the atmosphere of a rocky planet is more difficult to explain. The reported signal therefore attracts immediate attention. Perhaps unknown Venusian chemistry creates it. Perhaps volcanic activity contributes. Perhaps the measurement has another explanation. And perhaps organisms within the clouds produce the gas. The original study described an apparent phosphine spectral line in data from 2 radio observatories. The announcement is sometimes presented as evidence of life. The researchers themselves remain more cautious. A phosphine detection would not prove biology. It would identify a chemical mystery. The gas's origin would still need to be determined. Soon other teams reanalyze the data. Questions arise about instrument calibration, data processing, and whether sulfur dioxide could account for part of the signal. Different observations produce different results. Some analyses report possible phosphine at lower abundances. Others find no significant detection. An airborne observatory examining Venus at other phosphine wavelengths detected no phosphine and placed a low upper limit on its abundance in the atmospheric region it measured. The Venus story remains a debate about both measurement and chemistry. Is phosphine present at all? Does its abundance change with altitude or time? Could several instruments be observing different atmospheric layers? Could another molecule produce a similar spectral feature? If phosphine exists, can an unknown non-biological process explain it? Only after these questions are answered can biology be assessed. Future Venus missions may carry instruments directly through the clouds. A probe could sample droplets. It could measure acidity, water content, and complex molecules. It could examine whether cloud particles contain organized structures. An orbiter could map gases across the planet and watch how they change. Direct measurements would be far more informative than one distant spectral line. Until then, Venus offers a perfect example of the difference between a possible biosignature and proof. A possible biosignature is a beginning. It identifies something worth studying. It does not complete the story. Distant exoplanets create an even greater challenge. Their atmospheres cannot yet be sampled by spacecraft. Astronomers study them through thin traces within starlight. The signal from a small planet is faint. Clouds, instrument noise, stellar activity, and data processing choices can influence the result. One of the most discussed worlds is K218b. It orbits a small red dwarf more than 100 light-years away. The planet is larger and more massive than Earth. It belongs to a class often called sub-Neptunes, which is common elsewhere but absent from the solar system. Its true structure remains uncertain. It may possess a deep hydrogen-rich atmosphere above high-pressure material. It may contain a large water-rich interior. Some models suggest it could belong to a proposed class known as Hycean worlds, with hydrogen-rich air above a global ocean. Other models describe it as a gas-rich mini-Neptune without a habitable surface. The same basic measurements can therefore support different planetary pictures. James Webb Space Telescope observations detect methane in the planet's atmosphere. Early analyses also report carbon dioxide and a tentative hint of dimethyl sulfide, known as DMS. On Earth, DMS is produced mainly by living organisms, especially marine microorganisms. Its possible presence creates immediate excitement. A planet with an ocean, moderate temperatures, methane, carbon dioxide, and a biologically associated gas could resemble a distant inhabited world. But each part of that picture contains uncertainty. The existence of a liquid ocean is model-dependent. The atmospheric temperature does not guarantee a mild surface below. A thick hydrogen atmosphere can create high pressures and temperatures at depth. A molecule resembling DMS in a spectrum may be another compound with overlapping absorption features. The statistical strength of the original DMS hint is low. Further observations are needed. In April 2025, one research team reported new Webb mid-infrared data that it interpreted as evidence for DMS, dimethyl disulfide, or a combination of both at roughly 3 sigma statistical significance. The researchers emphasized that more observations were necessary, and that possible non-biological production pathways still needed investigation. A 3 sigma result can sound impressive. It means that, under the assumptions of a particular model, random noise is relatively unlikely to create the same feature. But scientific confidence depends on more than one statistical number. The chosen atmospheric molecules influence the fit. Different data reduction methods may slightly change the spectrum. Instrument systematics can create small patterns. Other molecules can absorb light at similar wavelengths. A result must remain stable when reasonable assumptions are changed. Independent teams soon perform broader analyses. One joint study of Webb's near and mid-infrared observations found insufficient evidence for DMS or dimethyl disulfide. The researchers reported that other carbon-bearing molecules could fit the same spectral region, and that the apparent preference depended strongly on data processing and model choices. Another extensive reanalysis confirmed atmospheric methane, but found no reliable evidence for DMS and did not require an ocean or biological explanation. Its models showed that the measured atmosphere could be consistent with a non-living, oxygen-poor mini-Neptune. K218b is, therefore, not proof of extraterrestrial life. It remains an important and intriguing planet. Methane is present. Its atmosphere can be studied across interstellar distance. The world may teach scientists how sub-Neptunes form and whether some can contain liquid water environments. Future observations may clarify the disputed molecular features. The planet deserves attention precisely because its interpretation is uncertain. The disagreement between studies is not a weakness in science. It is science working normally. Different teams use different analysis methods. They test whether a result survives independent examination. They explore molecules excluded from earlier models. They ask whether the instrument or the atmosphere creates a feature. Over time, the interpretations that best match all available evidence become stronger. A genuine biosignature should become clearer under deeper observation. It should not vanish whenever the data are reduced in a different reasonable way. Its associated molecules should form a consistent chemical environment. The proposed planet should possess conditions where biology can plausibly survive. Non-biological processes should struggle to reproduce the entire pattern. K218b may eventually provide such a pattern. It may instead become a lesson in the complexity of hydrogen-rich atmospheres. Both outcomes are valuable. The almost discoveries are not limited to planets and molecules. Objects observed within Earth's atmosphere also generate claims of extraterrestrial technology. These observations are commonly called unidentified anomalous phenomena, or UAP. The term describes something observed in the sky or another domain that cannot be immediately identified from the available data. It does not describe the object's origin. A UAP may later be identified as an aircraft, balloon, satellite, atmospheric effect, astronomical object, sensor artifact, or another ordinary phenomenon. Some cases remain unresolved because the information is incomplete. A distant light may be recorded for only a few seconds. A video may lack reliable distance and scale. A sensor may show an apparent motion influenced by camera movement. Weather information may be missing. Several observers may provide sincere but different descriptions. Without enough data, a conclusion cannot be reached. The remaining mystery is sometimes treated as evidence of something extraordinary. Scientifically, it is evidence of insufficient information. This does not mean that every observation has been explained. It means that unexplained cases have not demonstrated an extraterrestrial origin. These are different statements. An unidentified light is unidentified. It does not become an interstellar spacecraft simply because no ordinary object has yet been matched to it. The same rule applies throughout astronomy. An unexplained radio signal is not automatically artificial. An unexplained movement is not automatically advanced technology. The unknown should remain open until evidence narrows it. This careful language protects genuine discovery. If every unusual observation is announced as alien life, the important cases become difficult to distinguish from mistakes. Public attention rises quickly and fades quickly. Future evidence may be dismissed because earlier claims did not survive examination. Caution preserves meaning. When scientists eventually describe something as proof, the word should carry the weight of repeated measurement. UAP research can still improve scientific knowledge. Better sensors can record direction, distance, speed, weather, and spectral information at the same time. Standardized reporting can make cases easier to compare. Independent instruments can verify whether an object is physically present. Publicly available satellite and atmospheric data can help identify events. The goal is not to assume an explanation. It is to gather enough information that fewer observations remain ambiguous. The same principle guides astrobiology. Better data turn mysteries into objects. A faint signal becomes methane. A strange color becomes a mineral. A changing brightness becomes a cloud. Sometimes the explanation is familiar. Sometimes it reveals new natural science. And one day, it may reveal life. There have been many other moments when astronomical discoveries briefly appear artificial. Pulsars repeat with extraordinary regularity. Their signals once seem organized enough to suggest intelligence. They are now understood as rotating neutron stars. Fast radio bursts release immense flashes from distant galaxies. Some repeat in complex patterns. At least several are associated with highly magnetized stellar remnants. Unusual stellar dimming may suggest orbiting structures. Further observations often reveal dust. Each natural explanation expands the known universe. Nature repeatedly creates patterns that seem engineered when first encountered. It produces clocks, beams, pulses, rings, spirals, and repeating sequences. The universe is capable of order without intention. This makes the search more difficult, but also more beautiful. The background against which intelligence must be found is not simple noise. It is a cosmos filled with organized physical processes. To identify technology, science must find a pattern that nature does not readily create. To identify biology, it must find chemistry that remains out of balance for a meaningful reason. To identify fossils, it must find structures supported by geological and chemical context. Proof may require several independent forms of evidence. Imagine a future mission flying through the plume of Enceladus. Its instruments detect complex organic molecules. That would be interesting, but not enough. Suppose it also finds amino acids. Amino acids can form without life. Suppose the amino acids show a strong preference for one molecular orientation. Living systems on Earth display such preferences, but some non-biological processes may also create them. Suppose the molecules appear inside membrane-like compartments. Suppose those compartments contain repeating polymers that store information. Suppose their isotope patterns indicate sustained metabolism. Suppose several instruments detect the same organization in independent plume particles. The conclusion would grow through accumulation. No single observation would stand alone. The pieces would support one another until a biological explanation became simpler than every alternative. Proof of life on an exoplanet would develop in a similar way. A telescope might detect oxygen, Another instrument might confirm ozone. Methane might coexist in an atmosphere where geological production appears insufficient. Water vapor and moderate temperatures might indicate an ocean. Seasonal changes might reveal repeating biological cycles. Surface reflection might show a pigment pattern unlike minerals. Future observations might reproduce each result. Models of lifeless planets might fail to create the same combination. The conclusion would not rest on one molecule. It would rest on a planetary system of evidence. Proof of intelligence may have an even clearer structure. A narrow radio signal could repeat from the same star. Its frequency drift could match the motion of a known planet. The signal might contain mathematical modulation. Independent observatories could detect it. The pattern might encode increasing complexity. No satellite, instrument, or natural radio source could reproduce it. Such a signal would move beyond unexplained. It would carry evidence of design. Even then, science would proceed carefully. Receivers would be checked. Other observatories would observe simultaneously. The source direction would be refined. The signal's polarization and timing would be measured. Possible human interference would be examined. The greatest discovery would deserve the greatest patience. This is why there is still no confirmed proof that humanity is not alone. There are promising environments. There are organic molecules. There are planetary oceans. There are disputed gases. There are unexplained observations. There are statistical arguments suggesting that life may exist elsewhere, but none has yet crossed the full threshold. The absence of proof is sometimes mistaken for an absence of progress. In reality, progress is everywhere. Mars has changed from a point of red light into a mapped world with ancient lake beds. Europa has changed from a small moon into a possible global ocean. Enceladus has changed from an icy sphere into an active world releasing water, salts, phosphorus, hydrogen, and organic chemistry. Thousands of exoplanets have changed the galaxy from an imagined collection of suns into a known population of planetary systems. Webb can now identify molecules within atmospheres more than 100 light-years away. Radio observatories can examine millions of channels. Laboratories can study microscopic grains with extraordinary precision. The search is becoming capable of detecting what earlier generations could only imagine. Almost discoveries are part of that growth. Viking teaches that reactive soil can imitate metabolism. ALH 8401 teaches that water rock reactions can make organic material and lifelike mineral structures. Venus teaches that a single spectral line can become a long debate about instruments and atmospheric chemistry. K218b teaches that faint biosignature claims depend on data processing, molecular models, and independent analysis. UAP studies teach that unusual observations need high-quality measurements before their origins can be known. Each lesson closes one path toward error. The next search becomes more precise. The next instrument becomes more careful. The next claim begins from a stronger foundation. This process may seem slow. The universe has waited billions of years. The search can afford patience. A rushed answer would not satisfy the question. Humanity does not merely want a curious signal. It wants to know. Knowledge requires evidence that remains after excitement fades. It must survive new instruments. It must survive disagreement. It must survive better explanations. Real proof should become stronger as it is examined. The first discovery of extraterrestrial life may initially resemble one of these almost discoveries. It may appear as a faint spectral feature, a chemical reaction, a microscopic form, a short signal. The difference will emerge later. The observation will repeat. Independent teams will confirm it. Alternative explanations will slowly fall away. New measurements will fit the same biological or technological picture. What begins as a possibility will settle into evidence. Evidence will gather into understanding. Until that moment, the uncertain clues remain valuable. They show where to look. They reveal what instruments must measure. They teach how easily hope can shape interpretation. They also demonstrate that the search is no longer purely philosophical. Samples exist. Spectra exist. Signals exist. The question is being tested against physical reality. No accepted proof has yet arrived. But the universe has offered several quiet rehearsals. Each one prepares humanity to recognize the difference between something mysterious and something truly alive. And somewhere, perhaps within a plume, beneath ancient stone, or inside the thin light of a distant atmosphere, the clue that finally remains may already be waiting. The universe is too large to understand through intuition alone. Human experience develops on one planet. Distances are measured in footsteps, roads, and oceans. A journey lasting several days feels long. A century feels ancient. The scale of the cosmos belongs to a different kind of thought. Stars are separated by light years. Galaxies contain billions of suns. The universe has existed for billions of years. When the question of extraterrestrial life is placed inside this enormous setting, probability becomes impossible to ignore. Probability is not proof. A large number of opportunities does not guarantee that an event has occurred. A field may contain millions of stones without containing a diamond. Yet the number of opportunities still matters. If planets were exceptionally rare, then Earth might stand almost alone, simply because there were few other places where life could begin. Astronomy has now removed that possibility. Planets are common. Rocky planets are common. Water and organic chemistry are widespread. Stable environments may exist on planets and moons throughout the galaxy. The universe has created an immense number of experiments. Each world begins with different conditions. Some are too hot, some are too cold. Some lose their atmospheres. Some remain covered by deep oceans. Some contain active geology. Some orbit calm stars. Some experience violent changes during their youth. Most may never become alive, but the number of worlds is so large that even a rare biological event could happen repeatedly. This is not a conclusion. It is the central mathematical possibility behind the search. The Milky Way alone contains an extraordinary population of stars. Estimates vary because much of the galaxy is hidden by dust, and because faint stars are difficult to count. The total is thought to lie in the hundreds of billions. The exact number matters less than the scale. Each star represents a possible planetary system. Many possess several worlds. Small, cool stars are especially numerous and may remain active for immense periods. Larger stars shine brightly, but live shorter lives. Stars like the Sun occupy a middle region, stable enough to provide billions of years for planetary evolution. A single galaxy, therefore, contains more stars than any person could count one by one across a lifetime. And the Milky Way is only one galaxy. Modern observations reveal galaxies in every direction. Some are large spirals. Some are smooth elliptical systems. Some are small and irregular. They gather into groups and clusters. Great filaments of galaxies stretch across space, separated by enormous voids. The observable universe contains at least hundreds of billions of galaxies, and perhaps far more depending on how faint and distant systems are counted. Every galaxy carries its own history of stars, planets, chemistry, and time. The number of potential worlds rises beyond ordinary imagination. This scale does not make life certain. It changes the meaning of rare. Suppose life begins on only one planet among a million suitable worlds. That would make it extremely uncommon. Yet if the universe contains far more than a million suitable planets, life could still appear many times. Suppose complex life is rarer still. Suppose intelligence arises on only a tiny fraction of living worlds. The cosmic population may remain large enough for other technological civilizations to have existed. They might be separated by great distances. They might live during different periods. They might never communicate. Yet they would still mean that life and intelligence are not unique to Earth. The difficulty lies in assigning real probabilities. Science has one confirmed example of life: Earth. From one example, it is impossible to calculate how often biology begins. Perhaps the transition from chemistry to life is easy when liquid water and useful energy are present. Perhaps it depends on an event so unlikely that it occurs only once in the observable universe. Both possibilities remain compatible with current evidence. This uncertainty is sometimes hidden by confident estimates. Numbers can appear precise even when their foundations are weak. A calculation may produce 10 civilizations or 10 million civilizations, but the result depends on assumptions that are not yet known. The mathematics is valuable when it reveals which questions matter. It becomes misleading when uncertain guesses are treated as measurements. The most famous framework for thinking about technological civilizations is the Drake equation. Astronomer Frank Drake introduces it in 1961 while preparing for a scientific meeting about the search for extraterrestrial intelligence. The equation is not designed to provide a final answer. It organizes the problem. It asks how several probabilities might combine. How often do stars form? What fraction of stars have planets? How many planets per system could offer suitable environments? What fraction of those worlds develop life? What fraction of living worlds develop intelligence? What fraction produce detectable technology? And how long does that detectable phase continue? Each factor narrows the possibilities. Some can now be estimated far better than they could in 9. Planet formation is no longer speculation. Thousands of exoplanets have been confirmed. Surveys indicate that planets are a normal feature of the galaxy. Many stars appear to possess small worlds. Rocky planets occur across a wide range of systems. This part of the equation has become less mysterious. The biological factors remain almost completely open. No one knows the fraction of suitable worlds where life begins. No one knows how often simple cells become complex ecosystems. No one knows whether intelligence is a common evolutionary outcome or a rare accident. The final factor, the lifetime of detectable technology, may be especially important. A galaxy could produce many civilizations across its history, while containing very few at the same moment. A technological society may emit strong radio signals for only a short period. It may later become quieter. It may change communication methods. It may disappear. Its detectable lifetime could last centuries, millions of years, or something in between. A civilization that survives and communicates for a long time becomes much easier to encounter. One that exists briefly may pass through cosmic history without overlapping another. The Drake equation therefore connects biology with time. Distance alone does not separate civilizations. Their eras must also meet. The Milky Way is more than 10 billion years old. The Sun forms relatively late in that history. Many stars and planets are billions of years older than Earth. If life and intelligence are common, some civilizations could have had enormous head starts. A society only 1 million years older than humanity would be far older than all recorded human civilization. Its technology could follow paths impossible to predict. A civilization 1 billion years older would be separated from humanity by almost the full history of complex life on Earth. This age difference deepens the mystery of the quiet sky. If other technological species are common, some should perhaps have become visible long ago. Yet age also creates separation. An ancient civilization may have vanished before the Sun formed. Its radio signals may already have passed through this region of the galaxy. Its structures may have decayed. Its planet may have changed as its star evolved. The galaxy could contain traces of intelligence without containing the intelligence itself. Humanity may be looking for present neighbors inside a landscape shaped by ancient lives. The archaeological search for technology may therefore become as important as listening for active messages. A long-lasting structure could remain after its builders. Artificial objects placed in stable orbits might survive for immense periods. Industrial changes to a planet's atmosphere could leave temporary chemical records. Unusual isotope patterns might remain in surface materials. Large-scale alterations to a planetary system could persist. None has been found. The idea simply recognizes that civilizations, like organisms, may leave fossils. The cosmic record may contain technological archaeology. Probability also depends on the speed with which life appears. Earth forms about 4.5 billion years ago. Its earliest history is violent. The surface is hot. Large impacts occur frequently. The atmosphere and oceans gradually develop. Evidence suggests that life is present relatively early, once stable environments become available. The precise date remains uncertain because Earth's oldest rocks are rare and heavily altered. Still, life does not seem to wait until the planet is old. This early appearance may suggest that biology begins readily under suitable conditions. But one world cannot establish the rule. Observers necessarily find themselves on a planet where life began early enough for intelligence to evolve. If life had appeared very late on Earth, there might not have been enough time for humans to arise before the sun's increasing brightness made the planet less hospitable. This creates a selection effect. Humanity can only observe a history compatible with its own existence. The early arrival of life is encouraging. It is not decisive. The later stages of evolution create further uncertainty. Simple life appears early. Complex life takes much longer. For most of Earth's history, the planet belongs entirely to microorganisms. Cells without nuclei dominate ancient oceans. A major transition eventually produces complex cells containing internal structures. These cells are called eukaryotes. They include animals, plants, fungi, and many microscopic organisms. The origin of the eukaryotic cell may involve a partnership between simpler cells. One cell begins living inside another. Over time, the internal cell becomes the mitochondrion, the structure that helps complex cells obtain energy efficiently. This event, or series of events, may be one of the rarest transitions in Earth's history. Complex life depends upon it. If such partnerships are difficult to establish, the galaxy may contain many microbial worlds but few planets with animals. Multicellular organisms also evolve gradually. Cells must cooperate. They must communicate. They must control growth. They must specialize. Some become skin. Some become muscle. Some become nerves. A single genetic lineage turns into a coordinated body. This occurs more than once on Earth, suggesting that multicellularity can emerge through different paths. Yet large complex organisms remain absent for much of the planet's history. Oxygen levels, climate, ecology, and genetic innovation all influence their rise. Intelligence is a still narrower development. Many organisms solve problems. Birds use tools. Octopuses explore objects. Primates understand social relationships. Dolphins communicate and learn. Intelligence does not belong to one branch alone. Different forms evolve in response to different environments. Technological intelligence, however, requires more than problem-solving. It needs physical structures capable of manipulating the environment. It benefits from social learning. Knowledge must survive beyond one individual. Language or another information system must become sufficiently rich. Energy sources must be controlled. Materials must be shaped. A stable culture must accumulate discoveries across generations. Earth produces only one known species that builds radio telescopes. This may mean technological intelligence is rare. It may mean that humanity is simply the first example on Earth. Evolution has no predetermined destination. It does not move naturally towards cities, mathematics, or spacecraft. It responds to local pressures. A highly successful organism may remain simple for billions of years. Bacteria are not unfinished animals. They are extraordinarily effective forms of life. A planet covered in microbes can be biologically successful without ever producing a mind that studies the stars. The question is therefore not whether evolution always creates intelligence. It does not. The question is whether, across enough worlds and enough time, it creates intelligence more than once. The universe provides a vast number of opportunities. Probability also changes when hidden habitats are included. Early estimates focus mostly on Earth-like planets orbiting at suitable distances from Sun-like stars. Modern planetary science expands the list. Icy moons may contain oceans. Planets orbiting red dwarfs may maintain atmospheres. Rogue planets may preserve internal warmth. Subsurface environments may survive after a planet's surface becomes hostile. The habitable volume of the universe may be much larger than the number of visibly Earth-like worlds. Europa is not in the Sun's traditional habitable zone. Enceladus is even farther away. Yet both may contain liquid water. Tidal heating replaces strong sunlight. Ice provides insulation. Rock-water reactions may supply chemical energy. If life can begin in such oceans, then almost every planetary system containing giant planets and icy moons may offer additional habitats. The search no longer counts only planets. It counts environments. A single world can contain many separate settings. Warm ponds, deep oceans, rock pores, hydrothermal systems, ice-covered lakes, cloud layers, subsurface brines. Life may fail in one and begin in another. A planet that appears broadly inhospitable may contain a small region where chemistry remains stable for millions of years. The number of biological experiments may therefore be far larger than the number of worlds. Comets and asteroids add another dimension. Organic molecules form in space and become incorporated into small bodies. Impacts deliver these compounds to young planets. The early solar system is not a collection of completely isolated worlds. Material moves between them. Large collisions eject rocks from planetary surfaces. Some fragments enter space and later land elsewhere. Meteorites from Mars reach Earth. Material from Earth may also have reached Mars. This exchange raises the possibility of lithopanspermia. Microorganisms sheltered inside rock might survive ejection, interplanetary travel, and impact under certain conditions. No evidence shows that this has spread life between planets. Laboratory studies and natural meteorites demonstrate that physical transfer is possible. If life begins on one world, it may sometimes seed another. This would increase the number of inhabited environments without increasing the number of independent origins. A solar system could become a connected biological family. The possibility complicates future discoveries. If Martian microbes use DNA, familiar amino acids, and the same genetic code as Earth life, they may share an ancestor. Perhaps life begins on Mars and reaches the young Earth. Perhaps the direction is reversed. Perhaps both receive organisms from an earlier source. Finding similar biology would prove that life exists beyond Earth, but it would not necessarily prove that life begins easily. A truly independent biology would be more informative. It might use different genetic molecules. Its proteins could rely on a different collection of amino acids. Its cellular membranes might use an unfamiliar chemistry. Two separate origins within one solar system would greatly change estimates of life throughout the universe. It would mean that biology begins at least twice where a single star provides suitable environments. The probability of countless other origins would rise. This is why the search on Europa, Enceladus, and Titan carries such importance. These worlds are less likely than Mars to have exchanged substantial surface material with Earth. Their environments are physically separated. Life discovered in one of their oceans may represent a genuinely independent beginning. The smallest cell there would carry a mathematical message. It would transform one known origin into two. The step from 1 to 2 is enormous. With one example, every probability remains uncertain. With two independent examples in one planetary system, rarity becomes much harder to defend. The solar system would appear biologically productive. The galaxy would contain billions of similar systems. The conclusion would not prove that every suitable world is alive. It would show that life is not an event confined to one planet. At present, this second example does not exist. The mathematics must remain conditional. There is another approach to probability known as Bayesian reasoning. It begins with an initial expectation and updates that expectation as new evidence appears. Scientists may begin with different beliefs about how common life is. One researcher may think the origin of life is relatively easy. Another may suspect it is extraordinarily rare. As observations accumulate, both should adjust their expectations. The discovery of many rocky planets increases the number of possible habitats. Organic molecules in interstellar space show that prebiotic chemistry is widespread. Ancient water on Mars reveals that habitable environments once existed nearby. Subsurface oceans on icy moons expand the range of possible homes. Early life on Earth may modestly support the idea that biology begins without extreme delay. The lack of confirmed technosignatures may reduce expectations for loud, long-lived civilizations. Each clue changes part of the picture. None alone determines the result. Bayesian reasoning is useful because it treats knowledge as gradual. Science does not move only from ignorance to certainty. Confidence can increase or decrease in small steps. The universe may offer evidence long before it offers proof. A methane-rich atmosphere on a temperate planet could raise the probability of life. A second gas inconsistent with geology could raise it further. A repeating seasonal cycle could strengthen it again. A clear non-biological explanation might then lower it. The probability changes as the planetary story becomes more complete. This is how a future biosignature may be understood. Not as one miraculous announcement, but as a sequence of updates. The idea of mediocrity also influences scientific expectations. The Copernican principle suggests that Earth does not occupy a privileged central position. Earth is not the center of the solar system. The Sun is not the center of the Milky Way. The Milky Way is not the center of the universe. Humanity occupies an ordinary location within a vast cosmos. Some extend this principle to biology. If Earth's location, elements, chemistry, and physical laws are ordinary, perhaps life is also ordinary. This is a reasonable hypothesis. It is not proof. Earth may be ordinary in location and extraordinary in biological history. The Copernican principle cautions against assuming uniqueness without evidence. It does not guarantee similarity everywhere. The anthropic principle adds a different caution. Observers can only exist in environments compatible with observers. Humanity sees a planet with water, stable temperatures, complex chemistry, and long-term habitability because such a planet is required for humans to appear. This makes Earth difficult to evaluate. Its suitability may seem typical only because no one can arise on an unsuitable world to notice the difference. Imagine a vast collection of planets. Almost all are lifeless. A tiny number develop observers. Every observer naturally looks around and finds itself on one of the rare successful worlds. From its own perspective, the conditions seem normal. This selection effect means that Earth's habitability does not reveal how common habitable planets are. Astronomy must measure that directly. Exoplanet surveys begin to do so. They estimate how frequently rocky worlds occupy temperate orbits. They measure the properties of stars. They examine atmospheric survival. Future telescopes will study water, carbon dioxide, oxygen, methane, and clouds. The statistics will improve. Instead of guessing how many potentially habitable planets exist, science will build an observed population. The nearest examples will become individual worlds rather than entries in an equation. Some planets may challenge assumptions. A world outside the traditional habitable zone may remain warm beneath a thick atmosphere. A planet within the zone may be dry and airless. A red dwarf world may preserve an ocean despite stellar flares. A planet resembling Earth in size may possess a completely different climate. Each discovery will refine the probabilities. The search will move from broad estimates toward a measured cosmic ecology. There may be common lifeless planets, rare ocean worlds, frequent microbial atmospheres, and very rare technological signals. Or the pattern may be completely different. The data have not yet arrived. The idea of a cosmic lottery is often used to describe life. A planet receives many chances across time. Chemical reactions occur in oceans, sediments, ice, and rock. Molecules form and break apart. Some organize into networks, some store information, some become enclosed within membranes. Most combinations disappear. A small number may become self-sustaining. If each chemical attempt has a tiny chance of advancing toward biology, the number of attempts becomes crucial. An ocean contains an enormous number of molecules. Reactions happen continuously for millions of years. Hydrothermal systems create gradients. Shallow pools cycle between wet and dry. Mineral surfaces concentrate compounds. Ice gathers molecules into small liquid channels. The early Earth may host countless experiments at once. The origin of life would not depend on one molecule making one attempt. It would depend on a planetary system performing chemistry without rest. Other suitable worlds may do the same. The lottery metaphor remains imperfect. Chemical evolution is not purely random. Physics favors some structures over others. Certain molecules form more easily. Some reactions accelerate others. Membranes can assemble spontaneously from suitable compounds. RNA-like molecules can both store information and assist chemical reactions. Mineral surfaces can guide molecular organization. Once a system begins copying with variation, natural selection provides direction. Successful structures become more common. Life may emerge from a combination of chance, chemistry, and selection. The probability depends on pathways not yet fully understood. Laboratory research attempts to reconstruct pieces of this transition. Scientists create amino acids under simulated early planetary conditions. They study how nucleotides might form. They observe fatty molecules assembling into membrane-like bubbles. They investigate RNA molecules capable of catalyzing reactions. They explore metabolism-first models, genetic-first models, and systems in which several processes arise together. No laboratory has yet reproduced the complete natural origin of a living cell from simple planetary chemistry. This does not mean the transition is impossible. It means the historical process is still hidden. Earth erased much of its earliest record through geology. The first organisms were microscopic and delicate. Their molecules rarely survive for billions of years. The path must be reconstructed from modern biology, ancient rocks, chemistry, and experiment. Understanding that path would transform estimates of extraterrestrial life. If researchers discover a robust sequence that produces self-replicating systems under many plausible conditions, life may seem common. If every pathway requires an extremely narrow environment and a rare sequence of events, life may seem less likely. The probability is waiting inside chemistry. Time itself multiplies opportunity. The universe is about 13.5 billion years old. Earth is about 1/3 that age. Stars and planets exist long before the solar system forms. Some rocky worlds may have had billions of additional years for life and intelligence to develop. Others form later and remain young today. The universe contains planets at every stage. Some are still gathering from dusty disks. Some have newly formed oceans. Some may be in microbial ages resembling early Earth. Some may contain complex ecosystems. Some may have passed through technological periods. Some may orbit aging stars and approach the ends of their habitable eras. The galaxy is not synchronized. It is a mosaic of histories. This reduces the chance that two technological civilizations will exist at the same moment. It also increases the chance that life has appeared somewhere at some time. The question, "Are we alone?" can therefore mean several things. Is Earth the only planet where life has ever begun? Is it the only living world in the galaxy today? Is humanity the only technological civilization currently active? Is it the only intelligence that has ever existed? These questions have different probabilities. Microbial life may be common while technological civilizations are rare. Intelligence may have appeared many times in the past, while humanity remains alone at present. Several civilizations may exist now, but be separated by distances that prevent meaningful communication. The universe can be biologically crowded and observationally silent. This distinction helps explain the apparent conflict between probability and evidence. The numbers suggest many opportunities. The sky provides no confirmed answer. Both can be true. Life may be distant. It may be hidden. It may be microbial. It may belong to another time. It may communicate through methods that do not reach Earth, or it may truly be rare. The uncertainty remains because observation has only recently become capable of testing these possibilities. There is also the possibility that humanity's sample is biased toward large, obvious technologies. Radio searches look for transmitters. Infrared surveys look for substantial energy use. Atmospheric studies may detect industries only if they alter an entire planet. A small, efficient civilization could remain invisible. A society might live within one region and use little energy. It might prefer biological engineering. It might communicate through tightly directed beams. Its waste heat may blend into natural background. Its technology may be advanced precisely because it wastes little. The most successful civilizations may not be the most visible. Human assumptions often connect progress with expansion. More cities, more energy, more communication, more movement. Another species may define success through stability, restraint, or inner complexity. It may remain on one world for millions of years without building megastructures. Probability estimates based on human development would fail to describe it. The search must therefore remain broad. It should listen for beacons while studying atmospheres. It should examine unusual stellar systems while exploring nearby oceans. It should search for industrial chemistry without assuming industry is universal. It should remain open to signs not yet imagined. Still, science cannot search directly for everything imaginable. It begins with measurable possibilities grounded in physics. Radio waves, laser pulses, atmospheric gases, thermal radiation, artificial transits, surface illumination, unusual chemical imbalances. These are not predictions of what aliens must do. They are places where current instruments can begin. The probabilities will change as these searches grow. A century of silence across carefully examined nearby systems would carry more meaning than the present silence. 1,000 characterized Earth-like atmospheres without biosignatures would reduce expectations for obvious surface life. The discovery of even one convincing microbial atmosphere would increase them dramatically. Statistics require a sample. Astronomy is only beginning to build one. Perhaps the most powerful mathematical fact is simply that 0 and 1 are very different. At present, the number of confirmed living planets is 1. The number of confirmed technological species is 1. The entire debate rests on whether these counts remain 1 forever. A single independent cell on another world would change the first number to 2. A single confirmed artificial signal would change the second. Once a phenomenon occurs twice, uniqueness disappears. Science can begin comparing. What conditions are shared? What chemistry differs? Did both worlds use water? Did both use carbon? Did intelligence evolve through similar pressures? With 2 examples, biology becomes a cosmic science, rather than a science of one planet. The next discovery does not need to reveal a galaxy full of life. It only needs to break the solitude of the sample. The universe has provided countless places to look. Planets orbit nearly every kind of star. Moons hold hidden oceans. Organic compounds drift through interstellar clouds. Meteorites carry amino acids. Water forms before planets are complete. Chemistry has been unfolding for billions of years across environments beyond counting. These observations do not complete the proof. They establish the opportunity. The number of opportunities is the strongest reason many scientists consider extraterrestrial life plausible. Not because large numbers create certainty, because large numbers make repeated events possible, even when each event is rare. The universe may have tried the experiment of life more times than can be imagined. On most worlds, the chemistry may fade. On some, it may remain simple. On a smaller number, cells may fill oceans. On fewer still, organisms may become complex. And perhaps on a scattered collection of planets, matter may begin to study itself. Those worlds may be so distant that their light has not yet reached Earth. Their civilizations may be ancient memories carried through space. Their biospheres may be young and silent. Their oceans may contain only the first fragile cells. The mathematics cannot say which image is real. It can say that the stage is vast. It can say that the ingredients are common. It can say that time has been generous. It can say that Earth is not the only world where the experiment could occur. For now, humanity stands between probability and proof. Behind it lies one living planet and a history written in cells. Ahead lies a galaxy filled with worlds that have barely been examined. The numbers invite wonder, but they also invite patience. A universe with countless opportunities may still hide its answers well. Somewhere, perhaps, the second example already exists. It may circle a quiet red star. It may rest beneath the ice of a nearby moon. It may release oxygen into a distant atmosphere. It may send a signal that has not yet reached Earth. Or it may simply live, unseen and unaware, within an ocean under another sky. The mathematics does not reveal its location. It reveals why the search is worth continuing. After every planet, molecule, ocean, signal, and mathematical possibility, one fact remains. Humanity does not yet possess confirmed proof of life beyond Earth. There are promising environments. There are complex organic molecules. There are planets with water vapor in their atmospheres. There are hidden oceans beneath nearby ice. There are ancient Martian lake beds and chemical reactions that resemble parts of biology. There are signals that remain unexplained because too little information survives. But none has yet crossed the final boundary between possibility and discovery. That boundary is important. The universe is filled with unusual chemistry. It creates patterns that resemble living structures. It builds molecules used by biology without requiring organisms. It produces regular pulses, narrow beams, and sudden flashes through natural physical processes. A convincing discovery must therefore do more than appear unusual. It must remain convincing after every ordinary explanation has been tested. Proof would need to survive repetition. It would need to survive independent examination. It would need to become clearer as better instruments studied it. True evidence should not depend upon one photograph, one laboratory result, or one disputed line in a spectrum. It should form a connected pattern. Several observations should point toward the same biological or technological explanation. The first proof may come from somewhere close. A spacecraft could land on Mars and examine material protected beneath the surface. It could drill below the region most strongly altered by radiation. Inside an ancient sedimentary layer, it might discover microscopic structures arranged like colonies of cells. Shapes alone would not be enough. Minerals can grow into spheres, tubes, and filaments. The structures would need matching chemistry. They might contain complex carbon compounds concentrated in a way ordinary geology struggles to explain. Their carbon isotopes might show a pattern associated with metabolism. Their surroundings might record an ancient lake, spring, or groundwater system. Several instruments would study the same sample. Other samples from the same layer would reveal comparable features. The discovery would grow through agreement. A return sample could make the case stronger. Earth laboratories could examine individual mineral grains using instruments too large and delicate to place on a rover. Researchers could map molecules across microscopic surfaces. They could measure isotope ratios with extreme precision. They could study how organic material is connected to the rock's formation. Independent laboratories in different countries could repeat the analyses. Contamination would be investigated carefully. The chemical signature of spacecraft materials would be compared with the sample. Earthly microbes would be excluded. If the same biological pattern remained after every test, ancient Martian life might finally become the simplest explanation. That discovery would prove that life once exists beyond Earth. It would not necessarily prove that life begins independently. Earth and Mars exchange rocks naturally. Large impacts eject material into space. Some fragments travel from one planet to the other. A microorganism sheltered inside stone might survive part of that journey under suitable circumstances. Martian and terrestrial life could therefore share a common ancestor. The relationship could be revealed through chemistry. If Martian organisms use DNA, RNA, familiar proteins, and the same genetic code found on Earth, a shared history would become possible. The organism would still be extraterrestrial in location, but life itself might have begun only once before spreading between planets. An independent origin would be even more informative. Martian biology might use a different genetic system. Its information-carrying molecules could have another structure. Its proteins might use unfamiliar building blocks. Its cells might maintain membranes through chemistry, unlike anything in Earth's biosphere. Such differences would suggest that matter has crossed into life through more than one pathway. The solar system would then contain at least two biological beginnings. One star would have produced several worlds and more than one origin of life. The implications would extend far beyond Mars. Billions of planetary systems contain rocky worlds, many formed from the same broad ingredients. If life begins independently twice within one small system, it becomes difficult to imagine that every other suitable system remains sterile. The strongest nearby proof may come not from Mars, but from an icy moon. Enceladus already releases material from its hidden ocean into space. A future spacecraft could pass through those plumes repeatedly. It might collect fresh ice grains and examine them before radiation changes their chemistry. The spacecraft would search for more than organic molecules. Organic molecules are common in space. Amino acids alone would also be insufficient. Meteorites contain amino acids formed without organisms. The mission would search for organization. Life selects and arranges molecules. Earthly proteins use a particular molecular orientation. Genetic systems build repeating chains with meaningful order. Cell membranes organize fats into enclosing layers. Metabolism leaves characteristic ratios among related compounds. A plume sample containing one of these patterns would be intriguing. A sample containing several would be much stronger. Imagine that ice grains contain compartments resembling membranes. Inside them rest long molecular chains with repeating units. Those chains carry complex arrangements rather than random mixtures. Amino acids display a strong and consistent orientation. Carbon isotope patterns suggest that some process repeatedly favors lighter forms. The same structures appear in plume particles collected on several separate passes. They are absent from control samples and spacecraft surfaces. No known water-rock reaction can create the entire collection. At that point, biology would become difficult to avoid. Scientists might still use careful words. They might announce evidence consistent with life. Further missions would attempt confirmation. Laboratories would reproduce possible non-living processes. Alternative chemical pathways would be explored. But if every test strengthened the same conclusion, Enceladus could provide the second genesis. A dark ocean beneath Saturn's light might contain cells. They may gather around warm mineral surfaces. They may drift through water that has never touched open sky. Their world may possess no sunrise. Its surface remains frozen. Its organisms, if present, would know only water, rock, chemical energy, and the slow pull of Saturn's gravity. Life would not need continents or seasons. It would need only a place where information and energy can continue. Europa offers a similar possibility. Its ocean may be deeper, and its ice more difficult to cross. A lander could examine material brought upward by geological activity. An orbiter could map surface chemistry. A future probe might eventually reach a shallow reservoir or melt through the shell. Any discovery would require extreme protection against contamination. Spacecraft built on Earth carry microorganisms despite careful cleaning. Some microbes survive dry conditions, radiation, and long periods without nutrients. A mission searching for alien cells must not introduce its own. Planetary protection, therefore, becomes part of the evidence. The discovery is believable only when scientists can show that the organism does not arrive with the instrument. A genuine Europa organism should be adapted to Europa's chemistry. Its molecular patterns should differ from common contaminants. It should appear in several local samples. Its abundance might change with environmental conditions. It may show structures connected to reproduction, energy use, or repair. The evidence would need to describe a functioning system rather than a single familiar molecule. Life is not one ingredient. It is an organized process. It maintains a boundary. It uses energy. It stores information. It produces imperfect copies. Those copies vary. Some persist more successfully than others. Over generations, the population changes. A living system is matter participating in its own continuation. Proof should reveal some part of that continuation. A microscope image of a cell dividing would be powerful. A sample consuming one compound and releasing another in a repeated controlled pattern would be powerful. A molecule carrying heritable information would be powerful. Several of these discoveries together could become decisive. Titan may offer a stranger answer. Its surface contains lakes and seas of methane and ethane. Its atmosphere continuously produces carbon-rich molecules. A hidden ocean of liquid water may rest far below the crust. If Titan contains life, it might occupy the subsurface ocean and use chemistry broadly comparable to other water-based environments. But its surface raises the possibility of biology in a liquid other than water. No known organism uses methane as its main cellular solvent. The chemistry would need to operate at extremely low temperatures. Reactions would proceed slowly. Cell-like boundaries would require molecules different from the fats used by Earth's organisms. This possibility remains speculative. Still, Titan allows science to ask whether life must follow the only example currently known. Alien biology may be recognizable through function rather than ingredients. It may maintain order. It may consume environmental energy. It may alter local chemistry. It may reproduce with variation. But its molecules could be unfamiliar. A mission expecting DNA, proteins, and water-filled cells might overlook it. The search must remain open without becoming limitless. A proposed life form must still obey chemistry and physics. It must have a way to store information. It must have a source of usable energy. Its structures must remain stable long enough to function. It must interact with its environment in measurable ways. Science can search for these universal needs, even when the exact molecules differ. The first proof may instead come from far beyond the solar system. Thousands of exoplanets have already been confirmed, while planets across the Milky Way likely number in the trillions. Among those worlds may be planets whose atmospheres are transformed by living organisms. A distant biosphere cannot be placed beneath a microscope. Its atmosphere becomes the sample. Light passes through its gases. Molecules absorb selected wavelengths. The spectrum travels across interstellar space and enters a telescope. A few missing portions of starlight may carry the first evidence of another living planet. Oxygen could form part of that evidence. On modern Earth, photosynthetic organisms continually replenish atmospheric oxygen. Without life, much of it would react with rocks, gases, and dissolved material. Yet oxygen can also form without biology. Ultraviolet light can break apart water molecules. Hydrogen can escape into space while oxygen remains. Carbon dioxide can also participate in photochemical pathways that produce oxygen. A distant oxygen detection would therefore begin the investigation rather than finish it. The planet's entire environment would need to be understood. Does it still contain water? Is its temperature suitable for liquid oceans? Does the atmosphere show signs of severe water loss? What kind of ultraviolet light arrives from the star? Are gases present that would support a non-biological explanation? One molecule cannot be separated from its planet. Methane could strengthen the case. Oxygen and methane react. When both exist together, continuing sources must replace them. On Earth, life plays a large role in maintaining this combination. A temperate planet containing water, oxygen, methane, and carbon dioxide might deserve extraordinary attention. The quantities would matter. The star would matter. The planet's geology would matter. Researchers would test whether volcanoes, impacts, ocean chemistry, or water-rock reactions can reproduce the measured atmosphere. If those processes fail, biology becomes more likely. Other clues might join the gases. Ozone could indicate a larger oxygen supply. Nitrous oxide might suggest an active nitrogen cycle. Cloud patterns could reveal a water cycle. A glimmer from the planet's surface might indicate broad oceans. Changes across its year could show gases rising and falling with seasons. Surface colors might include a sharp reflection pattern produced by light-harvesting pigments. No single feature would provide certainty. Together, they could describe a functioning biosphere. A distant world might show oxygen that continually reacts with methane. Its surface might contain liquid water. Its atmospheric composition might change with a regular biological rhythm. Its reflected light might reveal a pigment spread across continents or oceans. Every non-biological model might fail to maintain the same combination. At that point, scientists may conclude that the planet is alive. The evidence would be indirect, but indirect evidence can still be conclusive. No one has touched the interior of the Sun. Its structure is known through light, particles, vibrations, and physical models. Black holes are studied through their effects on surrounding matter and space-time. Atoms were accepted before individual atoms could be directly imaged. Science often knows unseen things through patterns they cannot produce any other way. An exoplanet biosphere could be recognized through the same principle. The atmosphere would act as the collective product of countless organisms. Individual cells would remain invisible. Their combined chemistry would reach the stars. Confirmation would require time. Different telescopes would observe the planet. Several transits would be combined. Separate instruments would search for the same molecules. The host star would be monitored through periods of activity and quiet. Models would explore clouds, oceans, continents, and atmospheric circulation. The suspected biosignatures would need to persist. A single uncertain feature might disappear with improved calibration. A genuine planetary pattern should become richer. The world's atmosphere should begin to make sense as a connected system. The announcement may therefore unfold gradually. The first paper might describe an unusual chemical imbalance. A later observation could confirm water and oxygen. Another telescope might detect seasonal changes. Years of modeling could eliminate plausible geological sources. Eventually, the scientific language would shift. A possible biosignature would become a probable biosphere. A probable biosphere could become the first accepted evidence of life beyond Earth. There may be no single morning when the answer suddenly changes. Understanding may settle quietly, one spectrum at a time. Proof of intelligence could arrive more abruptly. A radio telescope might detect a narrow signal from the direction of a nearby star. The signal might drift in frequency as a planet turns and orbits. It could disappear when the planet passes behind its star. It might return at regular intervals. Other observatories could point toward the system and detect it independently. The transmission could contain patterns that natural processes do not create. Prime number sequences might repeat. Information might be encoded through changes in frequency, timing, or polarization. A map of physical constants might emerge. Technosignatures can include narrow radio signals, laser emission, artificial infrared excess, unusual transit patterns, or artifacts. A natural radio source can be highly regular. Pulsars provide the clearest example. A technological signal would need something more. Its structure might contain layered information. It might correct its own errors. It might change after a predictable astronomical event. It could respond to a transmission from Earth, though any exchange would be limited by light travel time. The strongest initial proof would be repeatability. The same signal would return from the same celestial coordinates. Its motion would match a planetary system. Observatories on different continents would detect it. Local interference, satellites, and equipment would be excluded. The pattern would remain after every technical check. If recognizable information appeared inside the signal, the conclusion could become immediate. Another intelligence would have arranged energy deliberately. The message might be simple. It may contain only a beacon. A repeated pattern could say nothing more than presence. There may be no images, language, or explanation. Still, intentional structure would be enough. Matter elsewhere has become capable of mathematics and transmission. A civilization has existed. The sender may be close in astronomical terms and still separated by decades. A star 50 light-years away is observed as it was 50 years earlier. A message transmitted from there today would not arrive for another 50 years. If humanity sends a reply, another 50 years pass before it reaches the source. The first exchange may unfold across centuries. The civilization could change during the conversation. The sender may no longer be listening. The signal could be an automated beacon built long before its discovery. It might be the technological equivalent of a fossil. Even so, it would answer the central question. Intelligence has arisen at least twice. Proof could also come from a laser. A brief pulse may outshine a star at one precise wavelength. If it repeats in an artificial pattern, natural explanations may become inadequate. Large engineered structures could produce unusual transit shapes. Extensive energy collection might cause a star system to release unexpected infrared heat. Artificial atmospheric gases could reveal industrial activity. Lights on a planet's night side might display organized patterns. Each possibility has natural alternatives. Dust produces infrared radiation. Planetary rings create complicated transits. Auroras and lightning generate light. Atmospheres create unexpected chemistry. The evidence must again become a pattern rather than an anomaly. No confirmed alien signal has yet been identified. This silence does not reveal how many civilizations exist. Searches have explored only part of the sky. Only selected frequencies have been examined with high sensitivity. Many stars have been observed briefly. Signals may be weak, intermittent, or tightly directed. Civilizations may not broadcast. Their periods of detectable technology may not overlap with humanity's. The search remains a small opening into an enormous space of possibilities. A confirmed signal would create practical questions. Who verifies it? Who announces it? Who studies its content? Who decides whether Earth should reply? International SETI protocols emphasize independent confirmation, open sharing of evidence, and broad international consultation before any response is sent. These principles recognize that the discovery would belong to no single observatory or nation. It would concern the entire planet. A message might contain knowledge. It could contain mathematics, astronomy, or a description of another biology. It might be impossible to interpret. Humanity could recognize intentional structure without understanding its meaning. Decoding may require years or generations. A signal designed for unknown receivers may begin with simple relationships. Numbers could be represented through repeated pulses. Atomic transitions could define units. Geometric patterns could build a common vocabulary. Images might be arranged through grids of binary information. More complex concepts would follow only after shared foundations were established. Yet there is no guarantee the sender thinks through symbols in a familiar way. Its senses may differ. Its environment may shape categories unknown on Earth. A species living beneath an ocean may organize space, time, and objects differently. A machine intelligence may not experience a biological world at all. Meaning is more difficult to transmit than energy. Even an undeciphered signal would change humanity. The night sky would no longer represent only stars, planets, and physical processes. It would contain known intention. At least one point of light would be connected to thought. The sender may never visit. No conversation may occur. The knowledge of its existence would still alter philosophy, religion, science, and culture. Human history contains many changes in perspective. Earth moves from the center of creation to one planet orbiting one star. The Sun becomes one member of a galaxy. The Milky Way becomes one galaxy among countless others. The elements within the body are traced to ancient stars. Life becomes part of a long evolutionary history. Another living world would continue this widening view. Earth would remain precious. Its oceans would remain beautiful. Human lives would not become smaller in meaning. Uniqueness and value are not the same. A forest does not become less valuable when another forest is discovered beyond a mountain. A second living world would not reduce Earth. It would reveal that the universe can become alive in more than one place. The discovery of simple microbes may appear modest beside the idea of an advanced civilization. Scientifically, it could be equally profound. A single independent cell would answer the oldest part of the question. Biology is not an isolated accident. Chemistry can awaken elsewhere. Evolution can begin on another world. Once that fact is known, the galaxy changes. Every suitable planet becomes part of a demonstrated pattern. Every hidden ocean becomes more than a possibility. Life may still be rare. Intelligence may remain extraordinarily uncommon. But the universe would no longer be known through only one biological example. The cell might also transform medicine and biology. Its molecules could reveal new ways of storing information. Its proteins might fold differently. Its metabolism could use chemical pathways absent from Earth. It might contain structures that solve biological problems through unfamiliar methods. Comparison would help scientists understand which features of Earth life are universal and which are accidents of history. Does all life use carbon? Does all life need a liquid solvent? Does evolution repeatedly create cells? Does genetic information always rely on long molecular chains? Does metabolism always use electrical and chemical gradients? One independent biosphere could begin answering these questions. A technological signal would reveal less about basic biology unless its content described the sender. It would instead establish that evolution can produce intelligence, culture, and engineering elsewhere. This would provide a second example of matter becoming aware of the cosmos. It would show that the universe does not only form stars and planets. Under some conditions, it forms beings capable of studying stars and planets. The discovery may also reveal that intelligence is temporary. The signal could come from the past. Its source world may no longer support its civilization. Every transmission carries a date. A message from 1,000 light-years away describes a society as it existed 1,000 years earlier. Astronomy always looks backward. Contact would therefore begin with history. Humanity may discover not a neighbor in the present, but an ancient voice still crossing space. A long-lived beacon could continue after its creators. Machines might preserve their knowledge. The civilization could design a message to outlast planets, governments, and biological generations. It might repeat for millions of years, waiting for any listener to develop suitable instruments. Such a message would be less like a conversation and more like a library. Its purpose might be simply to prevent knowledge from disappearing. Another civilization may already have faced the same silence. It may have wondered whether intelligence exists elsewhere. It may have built a transmitter and released a patient signal. The builders would not know who receives it. They would not know what shape the listener takes. They would trust only that physics is shared, and curiosity may arise again. Humanity's own search follows the same hope. Radio telescopes listen without knowing the language of a possible sender. Planetary missions travel to oceans hidden beneath ice. Spectrographs separate faint atmospheric signals from starlight. Laboratories reconstruct the chemistry that may precede the first cell. The methods are different, but the purpose is shared. They search for a second beginning. The answer may remain absent for a long time. Some questions are larger than one generation. The first people who study Mars do not expect to walk through its ancient lakes. The first astronomers who imagine planets around other stars cannot measure their atmospheres. Knowledge grows through instruments inherited and improved over time. A telescope begins with mirrors, shaped by one generation. Its observations guide the next mission. A disputed result reveals which measurement is needed later. The search continues through accumulation. Failure to detect life on one world would not end it. Mars may be sterile while Europa is inhabited. Europa may be sterile while another planetary system contains life. 100 lifeless atmospheres would not prove that all atmospheres are lifeless. They would improve estimates. They would reveal which environments fail. They would narrow the search. Silence is also data when enough of it is collected carefully. Perhaps life begins rarely. Perhaps complex cells require an unusual series of partnerships. Perhaps stable planetary climates are uncommon. Perhaps technological civilizations exist only briefly. If repeated searches continue to find nothing, these possibilities gain weight. Earth's living history would appear increasingly unusual. That conclusion would make the planet no less wondrous. It would make its preservation even more important. If Earth is one of very few living worlds, then every ecosystem carries cosmic significance. Every forest, ocean, microbe, and human mind would belong to a rare bloom of organized matter. If life is common, Earth remains valuable as one unique expression of it. Either answer deepens responsibility. The search for alien life ultimately returns attention to home. Earth possesses water in 3 familiar forms. It contains moving continents, a protective atmosphere, and a long-lived source of sunlight. Its biosphere reaches from upper clouds to deep rock. Life has persisted through immense environmental changes. Cells have become reefs, forests, animals, and mines. One branch has learned to reconstruct the planet's past and examine the atmospheres of distant worlds. The proof that life can exist in the universe is already present. It moves through every living cell on Earth. The remaining question is whether the universe has repeated the achievement. The evidence assembled so far does not answer with certainty. It answers with possibility. The elements of life fill space. Organic molecules form before planets. Water gathers in comets, rocks, moons, and atmospheres. Planets are abundant. Some orbit within temperate regions. Some maintain hidden oceans beyond those regions. Life on Earth survives heat, cold, salt, acid, pressure, darkness, dryness, and radiation. Mars once contains lakes and rivers. Europa and Enceladus hold water beneath ice. Titan performs complex organic chemistry beneath its orange haze. Distant atmospheres can now be measured. Radio and optical instruments can search for technology. The universe has provided many stages. No confirmed second performance has yet been observed. This is not proof that humanity is alone. It is a description of present knowledge. The answer remains open. Somewhere in the Milky Way, chemistry may already be carrying information from one generation of cells to the next. A world may contain oceans whose color is shaped by unfamiliar pigments. A quiet moon may shelter organisms near warm stone. A distant civilization may measure the sun as a small yellow star and wonder whether its planets are alive. Its instruments may be only slightly less sensitive than those on Earth, or its search may have begun millions of years earlier. Two living worlds could exist without knowing the other is present. Distance can preserve solitude even when solitude is not real. Light requires time. Signals weaken. Planets hide beside bright stars. Organisms remain beneath soil and ice. The universe does not make its living places easy to find. Still, the search has moved from imagination into measurement. The instruments now exist. The samples are being gathered. The atmospheres are being studied. The sky is being listened to. Humanity may not discover life tomorrow or within one lifetime, but the question is no longer beyond science. It waits within real data. Perhaps proof will arrive in a grain of ice. Perhaps it will be preserved inside Martian stone. Perhaps it will appear as two gases sharing the air of a distant world. Perhaps a thin radio tone will cross the galaxy and repeat. When that evidence comes, it may seem small. A microscopic structure, a line in a spectrum, a pattern of pulses, yet inside that small observation will rest an enormous conclusion. Earth is not the only place where the universe has become alive. Humanity is not the only way matter has learned to wonder. Until then, the stars remain neither empty nor inhabited within confirmed knowledge. They remain open, and sometimes, an open question is not a silence. It is an invitation to keep looking. The universe has spent billions of years forming stars, worlds, oceans, and chemistry. The search has only just begun. The universe is larger than any single answer, and richer than any single world. Its stars carry planets, its moons shelter oceans, and its darkness holds the same elements that eventually become life on Earth. But for now, you do not need to travel any farther. Let the distant planets grow soft in your mind. Let the hidden oceans settle beneath their quiet coverings of ice. Let every unanswered signal fade gently into the background. Your breathing can become slower now. Your shoulders can rest. You have crossed ancient Mars, past the clouds of Titan, and drifted among worlds circling faraway stars. You have listened for quiet signals and followed the chemistry of life into the spaces between suns. There is nowhere else you need to reach tonight. The universe will continue turning without effort. Stars will continue glowing beyond the window. Planets will continue following their patient paths. And somewhere, perhaps, another living world will continue beneath its own peaceful sky. The answer does not need to arrive before morning. The question can remain among the stars while you rest. And if you are still awake and would like to keep drifting, another quiet journey is waiting for you on screen. If these calm nights bring you a little peace, you are always welcome to return, and to wander gently through science and the cosmos again, one drifting mind at a time. Sleep well, and good night.